the center of the Milky Way, our black hole is doing something it shouldn't, flickering like a wounded star, twisting light into impossible shapes. Every pulse from Sagittarius A feels like a message, and the timing is wrong. Is this a glitch in spacetime, or the first crack in what we think a black hole is? In the Milky Way's buried core, the laws of nature are being stress-tested at their absolute breaking point. Sagittarius A is not merely an object sitting quietly at the center of our galaxy. It is something far more consequential. It is a courtroom where gravity must testify under oath, where every measurement becomes evidence, and where the universe either confirms what we believe or forces us to begin again from scratch. From Earth, the galaxy looks serene. A bright river of stars arcs across the night sky, indifferent to our questions and immune to our clocks. The Milky Way stretches overhead in clear skies like a luminous spine, ancient and calm, offering no hint of what churns at its heart. Yet toward the galactic center, something changes dramatically. Dusk closes like a curtain pulled shut by unseen hands, and visible light simply fails to arrive. The photons that should carry information about the core never reach our telescopes. They are absorbed, scattered, and consumed by the thick interstellar medium that lies between us and the most violent, most extreme environment in our cosmic neighborhood. To see what lives behind that curtain, astronomy is forced to change languages entirely. Radio waves, infrared radiation, and millimeter wavelengths become our eyes where ordinary light has surrendered. We do not watch the galactic center directly the way we might watch a sunset or a distant mountain. We reconstruct it from fragments, from delays, from polarization signatures and frequency shifts. An image assembled from what survives the long, brutal journey across tens of thousands of light-years of space, gas, dust, and magnetic turbulence. At the heart of that reconstruction sits Sagittarius A*, a name that sounds clinical, but describes something almost mythological in its scale and strangeness. 4 million solar masses pressed into a region smaller than our own solar system. 4 million times the mass of our Sun, concentrated so densely that spacetime itself bends catastrophically around it. It anchors the orbits of the S-stars, those fast-moving stellar bodies that race around the galactic center like planets around a sun, except that these planets move at thousands of kilometers per second, and their sun is an invisible gravitational titan. It bends time for anything that dares to pass close enough to feel its influence. It turns space into a lens capable of duplicating images, stretching light into arcs, and folding photon paths back on themselves in ways that seem to violate every intuition we have ever developed about how light should behave. And still, amid all that certainty, amid the carefully measured mass and the precisely tracked stellar orbits and the decades of accumulated observations, one stubborn feature refuses to behave like a mere footnote in the textbook. It appears, it disappears, and it returns, carrying with it a kind of structure that should be erased by chaos long before it reaches our instruments. Something in the signal suggests either an overlooked order hiding in the maelstrom of the inner accretion flow, or a deeper rule that we have not yet named, a principle that our current equations are not equipped to express. This investigation follows the anomaly the way science must, not as mythology dressed in numbers, but as a chain of measurements that either holds together or breaks apart under scrutiny. We will build the baseline that general relativity predicts for black holes operating in strong gravity regimes. Then we will ask which parts of the observed signal belong to instruments, which belong to plasma, and which belong to the black hole itself, because in this region, the word near is extraordinarily dangerous. Near means minutes of orbital time compressed into a space smaller than the distance between Earth and the Sun. It means extreme magnetism so powerful that it shapes the trajectory of matter and light alike. It means matter heated until it becomes a luminous, turbulent fluid that radiates across wavelengths from radio to X-ray. Near also means that light can loop, stall, and return to the observer carrying information that has been edited by curvature itself. A photon does not simply travel in a straight line near Sagittarius A. It negotiates with spacetime at every step of its journey, and the negotiation leaves marks that careful analysis can read. If the anomaly is real, if the pattern persisting in the data reflects genuine physics rather than calibration error or statistical coincidence, then it is not merely a curiosity sitting at the center of our galaxy. It becomes a lever capable of prying at the boundary between classical gravity and the quantum world. It becomes a key to the question of whether event horizons are as final, as absolute, as permanent as we have always said. The horizon is supposed to be the end of the story for information, the point beyond which nothing returns and nothing communicates. If something is communicating back, even subtly, even encoded in a flickering pattern of infrared photons, then our story about horizons may need a new chapter. But before we reach for new physics, before we allow ourselves the intellectual excitement of paradigm shifts and revolutionary discoveries, we will do what the best scientific investigations have always demanded. We will try to make the mystery disappear. We will test rigorously whether the pattern can be forged by calibration errors, by sparse temporal sampling, by Earth's turbulent atmosphere distorting our measurements, or by the restless plasma whether that swirls around Sagittarius A in a constant magnetized storm. And if the pattern survives those trials, if it endures the scrutiny of independent instruments, independent teams, and independent analysis pipelines, then we will widen the hypothesis space without abandoning rigor. We will consider what else could mimic a black hole's mass and silence, while subtly changing what returns to distant observers. Objects that look almost identical from far away, yet differ profoundly at the edge where matter meets the horizon. Objects whose existence is permitted by the mathematics of general relativity, but whose physical reality remains unconfirmed by any observation we have yet made. Every step in this journey is a wager against our own expectations. Either the anomaly is a rare window into the most violent, hidden dynamics of warped spacetime, showing us the near-horizon environment in unprecedented detail, or it is the first sign that our clean equations have left something out, that gravity in its strongest form does not quite behave the way we have assumed. In the end, the central question is not whether the universe is strange. The universe is demonstrably, relentlessly strange. The question is whether the strangeness we are seeing is confined to the plasma and magnetism we can model, or whether it reaches deeper into gravity itself, where time, information, and physical reality may not agree on what the word inside even means. The Milky Way looks calm from here. A pale river of stars arcing across the night, peaceful in the way that only vast distances can make violent things appear peaceful. Yet its center is sealed behind dust, wrapped in soot, cut through by dark lanes that interrupt the bright band of light like shadows cast by something enormous. Visible light dies in those long, cold corridors between us and the core. It is absorbed and scattered by dust grains no larger than particles of smoke, grains so tiny and so numerous that they form an opaque wall across tens of thousands of light years. The place that should be brightest, the gravitational anchor of the entire galaxy, becomes a blind spot in the optical sky. And that absence is itself the first clue, the first indication that something significant is being hidden. To reach the galactic center, astronomy changes languages and learns to listen in other bands of the electromagnetic spectrum. Infrared radiation slips through dust that blocks starlight because longer wavelengths weave between dust grains instead of crashing into them. Infrared photons have the right size relationship to dust grain geometry to slide past where optical photons cannot. In infrared images, the sky toward the core stops looking empty and becomes crowded with dense starfields stacked in depth. Hot gas glows there as well, warmed by shocks, by collisions between stellar winds, and by the slow grinding of gravity-compressing material that has no choice but to fall inward. Radio waves travel farther still, tracing magnetic fields and compact sources that we cannot resolve in the optical. At some radio frequencies, even the dust itself becomes transparent, and the galaxy's hidden architecture begins to reveal itself in earnest. Filaments of ionized gas stretch for light years. Compact radio sources burn bright against the cooler background. Structures that would be invisible to an optical telescope announce themselves clearly in the radio sky, drawing a map of the center that visible light was never allowed to show. X-rays arrive only from violence. They come from shocks, from particles accelerated to relativistic energies by magnetic fields, from electrons spiraling in those fields and radiating through a process called synchrotron emission, and from gas heated to millions of degrees as it plunges inward toward the black hole. They carry the signature of absorption as well, because intervening material bites chunks out of the X-ray spectrum in ways that depend on the composition and column density of the absorbing material. Each wavelength band is a partial confession, an incomplete statement about what is happening at the center, and the full story requires all of them simultaneously, read together like overlapping translations of the same ancient document. The galactic center is not one picture, but a layered composite, assembled from different kinds of light, each sensitive to different physical processes and different regions of the environment. To understand it requires holding multiple images simultaneously, recognizing where they agree and where they contradict, and building from that comparison a consistent physical picture. At the heart of this obscured region sits Sagittarius A, a compact radio source first noticed as radio astronomy matured during the 20th century. It is small on the sky, almost lost amid brighter and more extended structures, but it anchors the galaxy's gravitational map with a kind of authority that no other object in the Milky Way can match. Early surveys could not see a black hole directly, so they searched for the consequences of one. They looked for the effects of extreme gravity on surrounding matter and light, building an indirect case from circumstantial evidence that accumulated over decades of patient observation. For many years, Sagittarius A was a candidate, a suspicion built from careful inference rather than direct detection. The evidence was good but not conclusive. The mass was large and concentrated, but alternatives to a black hole could not be definitively ruled out. The source was compact, but compactness alone does not prove an event horizon. The case grew stronger year by year, measurement by measurement, until it reached the threshold where reasonable doubt became unreasonable. Now Sagittarius A is not a suspect but a confirmed reality, the nearest supermassive black hole to Earth and the best nearby laboratory for the physics of extreme gravity. The mass of Sagittarius A is not guessed from its brightness. The source is faint and variable, and much of its power emerges outside visible light, making luminosity-based mass estimates unreliable. Instead, the mass is measured from motion, from stars that orbit an invisible center with clockwork precision that reveals the gravitational field they are embedded in. Their paths turn gravity into geometry and geometry into a mass estimate we can trust because orbital mechanics is among the most precisely tested branches of physics. In practice, astronomers fit orbits to observed stellar positions over many years, infer the central gravitational pull required to produce those orbits, and watch the same stars return on schedule to confirm the prediction. The process is meticulous and the results are clear. There is a concentration of mass at the galactic center that behaves, gravitationally, like a single compact object. The most famous of the orbiting stars are collectively called the S-stars, and they are fast, close, and tracked year after year as they thread through the crowded nuclear star cluster that surrounds the galactic center. One of these stars, designated S2, completes an orbit in roughly 16 years. That may sound slow by human standards, but S2 covers an enormous path at extraordinary speed. At its closest approach to the central mass, S2 moves at thousands of kilometers per second, deeper in the central gravitational potential, where relativistic effects begin to matter measurably. Its orbit closes around empty space, and the emptiness behaves exactly like a single compact object containing 4 million solar masses. The star's light even shifts slightly in frequency near periapsis, the closest point of approach, a subtle but measurable nod to time dilation and gravitational redshift that general relativity specifically predicts for objects moving fast through strong gravitational fields. The orbits do more than weigh the center. They constrain its size. If 4 million solar masses were spread across a large star cluster, the cluster would glow, and it would not remain dynamically stable over cosmic time. Close encounters between cluster members would fling stars outward through a process astronomers call evaporation, dissolving the cluster on time scales much shorter than the age of the galaxy. If the mass were contained in a swarm of dark compact objects like neutron stars or stellar mass black holes, the swarm would also evaporate through gravitational encounters on relatively short timescales. The simplest survivor of these constraints is a single black hole, or an object that mimics one so perfectly that it cannot yet be distinguished from one. The evidence is not one measurement standing alone. It is a convergence of many independent observations, all pointing toward the same gravitational focus. Many stars, many epochs, one invisible anchor. A black hole is not a hole in the usual physical sense. It is a region of spacetime where escape becomes impossible, not because something physically prevents escape, but because the geometry of spacetime itself has changed so drastically that all future-directed paths lead inward. The event horizon is the boundary, the point of no return for matter and light. It is defined entirely by the geometry of spacetime, not by any material substance or physical barrier. Outside the horizon, photons can still leave the vicinity of the black hole, though their paths are bent and delayed by curvature, and some are trapped in looping trajectories for a time before escaping. Near the horizon, gravity reshapes time itself in ways that make the familiar rules of physics unrecognizable. The rules do not break, but they apply in a context so extreme that our intuitions, built from a lifetime of experience in weak gravity, become useless guides. What looks like a place in space is also a transformation in what the future means for anything that falls inward. This is perhaps the most difficult conceptual feature of black holes to convey. The horizon is not a wall. It is a change in the causal structure of spacetime. Once something crosses inward, every possible future for that object, every path through spacetime that time allows it to take, leads deeper into the black hole. There is no path that leads back out, not because escape is difficult, but because the geometry of spacetime makes outward directions impossible futures. Near the event horizon, the word near is not measured in kilometers, but in units of the black hole's mass, because mass sets the curvature scale. For Sagittarius A, the horizon scale is comparable in physical size to the orbit of Mercury in our solar system, packed into a region far smaller than the solar system itself. That comparison is deceptive in important ways because it compresses a familiar astronomical distance into an environment that differs from our solar system in every physical parameter. The distance is tiny, but the consequences are enormous because spacetime curvature rises sharply there, affecting every measurement, every trajectory, every photon that passes through. That is where general relativity is tested hardest, where the predictions of Einstein's theory are most constrained against the most extreme physical conditions the universe provides. And that is where surprises, if they exist, are most scientifically valuable, because a deviation from the predicted behavior in strong field gravity would be far more informative than any number of confirmations in the weak field regime, where the theory has already been exhaustively verified. Sagittarius A is not a steady beacon. It does not shine consistently like a lighthouse, or even like the active galactic nuclei in distant galaxies that can outshine their entire host galaxy. It is underfed by the standards of supermassive black holes, accreting at a trickle, compared with the blazing quasars that dominated the universe's middle age. Little cold gas reaches the very center in a steady supply. Much of what does arrive may be blown back out by turbulence and magnetic pressure before it can cross the innermost stable circular orbit and begin the final plunge inward. Most of the time, Sagittarius A glows weakly in radio and infrared wavelengths, producing a low persistent hum that speaks of accretion happening somewhere, but not dramatically. Then it flares, briefly, unpredictably, with varying intensity, as if a switch is thrown somewhere in the inner flow. The brightness can rise by factors of several over the course of minutes, then decay over hours, then return to quiescence until the next event. Flares are expected in turbulent magnetized plasma, and variability in active regions like this is not itself strange. In a magnetized accretion flow, magnetic fields twist, stretch, reconnect, and snap into new configurations, dumping energy into electrons that then radiate efficiently. What is strange is not that flares occur, but that a newly recognized pattern within those flares repeats with a consistency that chance alone cannot easily explain. Observers describe a recurring signature near the horizon scale, a pattern seen across multiple independent instruments and across multiple observing campaigns separated by months or years. It appears as timing structure in the flares, as polarization swings that rotate in a preferred direction, or as apparent motion in the sky that does not match the simplest models of turbulent emission. In some datasets, the flare peaks arrive with a quasi-periodic rhythm, not perfectly regular like a mechanical clock, but stubbornly clustered around a preferred cadence. The timing hints at a preferred physical time scale, like an orbital period, a precession cycle, or a repeating magnetic instability that keeps resetting the system. In other datasets, the polarization angle rotates rapidly during flares, as if the magnetic field geometry is twisting in a coherent loop rather than fluctuating randomly in all directions. Polarization carries information about magnetic field structure and about how light was processed during its journey. A random, turbulent magnetic field tends to produce polarization that averages down because contributions from different orientations cancel. A coherent, organized field can maintain strong polarization with a stable or smoothly evolving angle. When the polarization angle rotates systematically during a flare, it is telling a structured story, not a random one. In still other datasets, the centroid of the emission, the brightness-weighted center of the light distribution on the sky, appears to move during flares in patterns that resist simple interpretation as pure turbulent noise. The centroid traces paths that look, in some events, almost orbital, as if a bright region is circling the black hole at a radius set by the inner accretion flow's geometry. Each clue taken alone could be noise, coincidence, or artifact. The data live at the edge of what instruments can reliably measure, and frontier observations are always surrounded by uncertainty. Together, the clues form a pattern that is repeatable enough to demand attention and stubborn enough to resist dismissal. The key claim is not that Sagittarius A is exotic by nature. It is that a specific behavior persists when statistical reasoning says it should wash out. Standard pictures treat the inner accretion flow as chaotic, with turbulence and reconnection creating brief bright patches that orbit, shear, and fade without producing long memory in the system. The reported signature suggests a structure that survives that erasure, or a driver that resets the system with surprising consistency. That matters for a specific reason. The near-horizon region is where our models are most constrained and where the physics has the fewest places to hide from observational tests. The gravitational field sets preferred timescales for orbital motion, and those timescales can be calculated from the black hole's mass alone. If the observed pattern sits at the right timescale but evolves in the wrong way, then either the plasma is stranger than expected or the spacetime hosting it is. General relativity makes specific quantitative predictions for what light should do near a black hole. It predicts how photons bend as they pass through curved spacetime. It predicts how orbital periods change with radius and how they are affected by spin. It predicts the existence of a shadow cast by photon capture and a bright ring formed by photons that orbit near the critical radius before escaping. It predicts that the horizon itself is featureless and dark, with no surface to reflect light back outward, no texture to announce where one region ends and another begins. If a signal looks like it is bouncing, or returning with phase-lock timing, or anchored to a preferred direction across multiple observations, it forces a careful and systematic examination of every alternative explanation. Some effects can be produced by gravitational lensing alone, because lensing has a particular grammar. It produces specific relationships between the positions of multiple images, specific delay times between them, and specific polarization rotations. When those relationships are tested against the data, they either fit or they do not. The anomaly survives that test, at least partially, and the survival is what keeps the investigation alive. The observational challenge is severe and cannot be understated. The galactic center is crowded with stars and extended structures that contaminate measurements. It is distant enough that horizon-scale resolution requires continent-spanning interferometry. It is buried behind dust and intervening plasma that distort signals at every wavelength. The atmosphere introduces noise, especially at the millimeter wavelengths used by the Event Horizon Telescope. Every photon from the inner region is precious, and the source is both faint and fast-evolving. The relevant timescales are minutes to hours, so gaps in observing coverage matter enormously. A cloud above a telescope, a technical glitch at a critical station, a brief gap in the cadence can erase an entire important event or create the illusion of a pattern where none exists. The emission is polarized, so small calibration errors can masquerade as magnetic structure. The source changes with wavelength, so a flare in infrared may not match what an X-ray telescope simultaneously records. Coordinated observing becomes essential, and interpretation becomes a puzzle assembled from pieces that were collected under different weather conditions, from different continents, through different instruments, by different teams with different systematic errors. To attack that puzzle, astronomers built a toolkit that treats the galactic center as a multi-wavelength crime scene where every instrument plays a specific role and no single instrument can solve the case alone. At millimeter wavelengths, the Event Horizon Telescope links radio dishes scattered across the Earth into a virtual planet-sized instrument. The EHT aims to resolve horizon-scale structure by exploiting the interference of radio waves arriving at different stations. The spacing between stations determines the resolution, and planet-spanning baselines provide micro-arcsecond resolution sufficient to detect the shadow predicted by general relativity. For Sagittarius A, the EHT must also contend with rapid variability that changes the source during the very hours needed to synthesize an image, complicating every reconstruction in ways that require careful algorithmic treatment. In the near-infrared, the gravity instrument on the Very Large Telescope Interferometer measures astrometry with micro-arcsecond precision. It can track the motion of bright flares, determining where the centroid of emission sits at each moment, effectively watching light move within the inner gravitational field on timescales of minutes. It can also continue tracking stellar orbits like S2, tightening the mass and distance estimates that set the geometric scale for all other observations. Gravity turns the inner region into a dynamic system with measurable motion rather than a static point source, and it gives the anomaly a stage where spatial patterns can be tracked quantitatively rather than merely inferred from brightness fluctuations. In X-rays, space observatories watch for the high-energy flares that signal the most extreme particle acceleration events in the inner flow. X-ray bursts can mark magnetic reconnection episodes or shocks where electrons are driven to energies far beyond what infrared emission alone would reveal. Their timing can be compared with infrared flare peaks to test whether the same electron population is responsible for emission across bands, or whether different physical processes operate at different energies. X-rays also probe absorption along the line of sight, providing additional information about the density and composition of intervening material. Long-term monitoring adds the fourth dimension to this investigation. Time across decades reveals whether Sagittarius A changes its statistical personality, whether flare rates drift seasonally or secularly, and whether any periodicity persists beyond a few observing campaigns. Long-term monitoring also exposes selection effects, The systematic biases introduced by the fact that we notice patterns more easily when we look harder and publish results that stand out from the background. A pattern that appears in one campaign might be a rare fluctuation that happened to occur when instruments were pointed. A pattern that appears across many campaigns separated by years becomes much harder to dismiss as coincidence. The hypothesis space for explaining the anomaly is broad and includes options that range from completely conventional to genuinely revolutionary. At one end of the spectrum, the pattern could be exotic plasma physics, a stable magnetic structure like a flux rope, or a standing shock that keeps reforming near the same radius in the accretion flow. Magnetic flux ropes are known from solar physics, where they can maintain their structure against turbulence for extended periods. Near a black hole, a similar structure might anchor the emission to a preferred location and produce repeating signatures when the viewing geometry aligns favorably. The pattern could arise from a precessing inner flow driven by the black hole's spin, imprinting a preferred timescale as spacetime drags the plasma around the rotation axis. Frame dragging, the effect by which a spinning mass pulls spacetime around with it, is a well-established prediction of general relativity that has been confirmed in weaker gravity environments. Near a supermassive black hole, frame dragging becomes extreme and can organize the motion of plasma in ways that produce repeating modulations in the observed emission. At the other end of the spectrum, the pattern could hint that the central object is not a classical black hole in the mathematical sense we have assumed. Alternatives to black holes exist in the theoretical literature, from boson stars to gravastars to various other compact objects that share the mass and compactness of black holes, but differ profoundly in what happens at and near the boundary that a black hole would have as its event horizon. A surface, even a very dim one, could add echoes or phase-locked signals that a true horizon would erase entirely, because a surface reflects or re-emits material while a horizon simply absorbs it. The question is not whether alternatives are theoretically fashionable. It is whether the data leave any room for them, and whether the anomaly represents a signal that only an alternative could produce while a classical black hole cannot. Before committing to either the conservative or the revolutionary interpretation, the investigation must establish the baseline expectations so precisely that deviations become unmistakable. To recognize an anomaly, we first build the picture of what should not be negotiable, what physics predicts firmly enough that a contradiction would carry real weight. Sagittarius A sits in strong gravity, where general relativity sets the rules for motion, time, and light without compromise. In the galactic center, strong gravity is not a metaphor used to convey drama. It is a precisely defined regime where spacetime curvature is measurable with current instruments, where Newton's gravitational approximation breaks down and must be replaced by Einstein's more complete description, and where the ratio of gravitational radius to physical size is large enough that relativistic effects dominate the dynamics. General relativity replaces gravity as a force with the curvature of spacetime. Mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. That description is elegant, but its consequences are practical and testable at every level. The how-to-move part translates into geodesics, the paths that objects follow through curved spacetime. These are the closest analogs to straight lines in a curved geometry, the natural paths that require no additional forces to maintain. A planet, a gas cloud, and a photon all follow geodesics, even though their experiences look wildly different to observers who track their trajectories. In the weak gravity of everyday experience, geodesics look like the straight lines of Euclidean geometry or the gentle curves of Newtonian gravity. Near a compact object with extreme curvature, geodesics become exotic. They can loop, spiral, and in some cases trace closed paths that return to their starting point. The geometry imposes itself on every trajectory without negotiation. A photon near Sagittarius A does not choose to bend. It follows the only path that spacetime's geometry allows, and that path curves in ways that no flat space intuition can predict. Coordinates that seem natural at Earth, the simple labeling of positions in space and moments in time that we use without thinking, become misleading near the black hole. Radial distance loses its obvious meaning. Simultaneity becomes relative to location in the gravitational field. Even the question of what happens at a particular moment depends on which observer is making the measurement and from where they are making it. This is not philosophical abstraction. It is a practical constraint on how we interpret the data that comes back from the galactic center. One firm prediction of general relativity is gravitational redshift, where light climbing out of a gravitational well loses energy and shifts to longer wavelengths. Photons emitted near the inner accretion flow leave the region stretched to longer wavelengths, carrying in their shifted frequencies a record of how deep in the gravitational potential they were produced. This redshift is not the light growing tired during a long journey. It is the precise accounting of energy in curved spacetime. A photon emitted deep in the potential well has a well-defined frequency as measured by a nearby clock in the same gravitational field. To a distant observer located far from the black hole where spacetime is nearly flat, that same photon arrives with a lower frequency, as if its color has slid toward the red end of the spectrum. The deeper the emission point, the stronger the shift. Another firm prediction is time dilation, where clocks located near a massive object run slower as measured by distant observers. Processes occurring near the horizon appear slowed when viewed from far away, even if locally, in the reference frame of the plasma itself. Nothing feels delayed or unusual. This creates a subtle but crucial distinction for interpreting observations. A flare can be brief in the reference frame of the plasma that produces it, yet appear stretched in duration when compared to a clock located far from the black hole. The plasma does not experience time dilation as anything unusual because it lives in its own local reference frame, but our measurements are made from the outside, where our clocks tick at a different rate, and the mismatch is encoded in the signal we receive. Light bending is the most visually dramatic prediction for imaging purposes. Photons follow curved paths through the warped spacetime near the black hole, so the black hole acts as a gravitational lens capable of magnifying and distorting the appearance of everything behind or around it. In weak gravity, the bending is a small correction that shifts a star's apparent position by a tiny angle. In strong gravity, bending becomes choreography. Rays skim the black hole, swing around it in arcs, and sometimes return toward the observer from directions that would be geometrically impossible in flat space. The lensing is not symmetric if the black hole rotates, and it is not gentle if the ray passes close to what is called the photon orbit, the critical radius where light can trace circular paths. A single bright patch of plasma can be duplicated into multiple images by this lensing, with each image corresponding to a different photon path that reaches the observer. Some paths are direct, while others involve the photon orbiting the black hole one or more times before escaping. Each duplicate image is delayed relative to the others and has a different apparent position and brightness. The result is that a single emitting region can appear to be in several places simultaneously to a distant observer, and the brightness of each image changes as the emitting region moves and as the lensing geometry shifts. These effects are not optional refinements that can be added after the basic picture is established. They fundamentally reshape every observable quantity in the near-horizon environment. They set the geometric framework within which every measurement must be interpreted, and they set the scale of what we mean when we say close to the black hole. For a 4 million solar mass object, the gravitational radius is roughly 6 million kilometers, enormous by everyday standards but microscopic on galactic scales. The relevant distances are a few Schwarzschild radii, and the relevant angles on the sky are tens of microarcseconds, requiring the most ambitious observational instruments humanity has constructed. The event horizon earns its name from the impossibility of receiving signals across it. It is not a surface made of any material. It does not glow or have a texture. It is a geometric boundary defined by the behavior of future-directed light cones in curved spacetime. Once a photon crosses inward, every future-directed path leads deeper in. This is what makes the region black, not an absorbing material, not a darkness imposed from outside, but a geometric structure that removes the possibility of outward escape. That creates a crucial observational rule that shapes everything in this investigation. We never see the black hole itself. We see the environment heated and accelerated around it. Everything we observe comes from the accretion flow, the soup of magnetized plasma that surrounds the black hole and radiates as it slowly spirals inward. The black hole is present only as an absence, a dark region where light does not emerge, surrounded by a glowing annulus that marks the inner boundary of the visible universe around it. Accretion is not a simple drain. In a simplified textbook picture, gas spirals smoothly inward like water down a bathtub drain, gradually losing altitude as it radiates away energy and angular momentum. The real process is nothing like that clean mental. It is a churning plasma where density, temperature, and magnetic field strength vary in 3 dimensions and across many timescales simultaneously. If we could somehow observe the galactic center from close range, the accretion flow would look mottled and alive. Bright knots would appear where the magnetic field compresses gas and heats electrons. Darker gaps would open where the plasma thins or cools, then close again as turbulence mixes the region back together. The pattern would never settle into a single stable shape because the underlying instabilities that drive accretion keep the system perpetually in motion. In many galaxies, accretion is bright because gas can cool efficiently by radiating energy as light. Those active galactic nuclei can outshine their host galaxies by factors of thousands, concentrating the power output of hundreds of billions of stars into a region smaller than the solar system. The physics of efficient accretion was developed partly to explain the extraordinary luminosities of quasars discovered in the mid-20th century. Their power demands an energy source more efficient than nuclear fusion, and gravitational accretion onto a supermassive black hole can provide exactly that efficiency, converting a significant fraction of infalling matter's rest mass energy into radiation. Sagittarius A is profoundly different from those bright systems. For 4 million solar masses, its luminosity is tiny, 10 orders of magnitude below what an actively feeding black hole of similar mass could in principle produce. That dimness is itself a clue that sets the character of the entire investigation, because mass sets the maximum potential for power output. If Sagittarius A were fed at the rate that powers a typical quasar, the galactic center would be a blinding beacon visible to the naked eye from Earth and would dramatically alter the appearance of the night sky. Instead, it whispers, and that whisper forces theorists to explain where the energy goes. The leading explanation is radiatively inefficient accretion. Much of the gravitational energy released as matter falls inward stays locked in the thermal energy of ions, which cannot radiate it away efficiently in the low-density environment near the galactic center. In a dense, efficiently radiating disk, energy is quickly transferred from ions to electrons, and electrons are efficient radiators that quickly convert thermal energy into photons. In a radiatively inefficient flow, the plasma is so tenuous that ions and electrons can become effectively decoupled. The ions hold most of the thermal energy but radiate poorly. The electrons, which do most of the radiating, receive less energy from the ions than they need to produce a bright output. Energy can also be carried inward by the bulk flow of matter, disappearing across the event horizon rather than shining outward as radiation. This family of accretion models describes a flow that is hot, tenuous, and inefficient at converting infalling matter into observable light. Hot in this context means something that violates everyday intuition. The temperatures can reach billions of degrees. Yet despite those extreme temperatures, the plasma is nearly collisionless, with particles traveling large distances before interacting. This changes how viscosity works, how heat moves through the system, and how the flow organizes its global structure. The accretion becomes a laboratory for kinetic plasma physics operating in regimes that cannot be reproduced on Earth. Low density matters for emission because the brightness of synchrotron radiation depends on the number of emitting electrons and their energy distribution. With fewer electrons, the plasma stays hot while radiating relatively little. The emission depends on how electrons are distributed in energy, whether they follow a thermal distribution that peaks at a characteristic energy, or whether they include a non-thermal tail of higher energy particles. In a dense plasma, collisions push particles toward thermal equilibrium quickly. In a tenuous plasma, non-thermal populations can persist for longer, and small pockets of accelerated particles can dominate the observed light even though they represent a tiny fraction of the total number of particles. Magnetic fields in the accretion flow are not passive participants. They are active agents that store energy, transport angular momentum, and control how electrons move and radiate. In an accretion flow, magnetic fields are amplified by differential rotation, which stretches field lines like taffy being pulled between rotating cylinders. The magnetorotational instability, one of the most important discoveries in accretion theory, turns that stretching into turbulence and enables the outward transport of angular momentum that allows matter to fall inward. Without this mechanism, gas would orbit indefinitely rather than accreting, and the black hole would remain dark regardless of its surroundings. Turbulence mixes the plasma, continuously regenerates and reorganizes magnetic fields, and creates the intermittent bright structures that produce the observed variability. Turbulence also creates a kind of statistical personality for the source. The accretion flow does not have a single deterministic state. It has a distribution of accessible states, and the observed brightness is a time series that samples that distribution. That matters for imaging because an interferometer does not take an instantaneous snapshot. It accumulates information over minutes to hours, while the source itself is continuously evolving. The synthesis image is therefore a time average of a living, breathing system, and features in that average must be interpreted carefully. From the baseline description of accretion physics, we can begin to predict what telescopes should measure and what constitutes a deviation from the expected behavior. We expect emission shaped by the combination of relativistic gravity and magnetized plasma physics. At radio and millimeter wavelengths, the dominant emission mechanism is synchrotron radiation produced by electrons spiraling in magnetic fields. The brightness and spectral slope of the synchrotron emission encode the energy distribution of the emitting electrons, the strength of the magnetic field, and the geometry of the emitting region. The millimeter band occupies a special position for Sagittarius A. At millimeter wavelengths, the galactic center becomes accessible through the veil that blocks shorter wavelength radio emission through a process called free absorption, and the interstellar scattering that blurs longer wavelength images becomes manageable. Millimeter emission can come from close to the black hole, because at this frequency, the accretion plasma is partially transparent rather than opaque. The combination of reduced scattering, partial transparency, and sufficient spatial resolution makes the millimeter band the primary window for horizon-scale imaging. In the near-infrared, flares arise from a smaller population of higher-energy electrons that are accelerated above the typical thermal distribution. These electrons emit synchrotron radiation at infrared wavelengths, and their presence above the quasi-steady background indicates that energy injection, likely from magnetic reconnection, has occurred recently enough that the electrons have not yet radiated away their excess energy. Infrared flares are diagnostically rich because they require specific conditions in the plasma, and their timing, spectral evolution, and polarization properties together constrain the acceleration mechanism. In X-rays, emission signals that particle acceleration has crossed a threshold even higher than what infrared emission requires. Very energetic electrons can produce X-rays either through synchrotron emission, requiring extraordinarily strong fields or extreme electron energies, or through inverse Compton scattering, in which lower-energy photons are boosted to X-ray energies by collision with fast electrons. The distinction between these mechanisms carries information about the plasma conditions, and correlating X-ray timing with infrared timing tests whether the same electrons are responsible for both. The spectrum across all these bands is not a single simple curve, but a combination of thermal and non-thermal components that evolve with time and with radius in the accretion flow. Different radii contribute different temperatures, densities, and magnetic field strengths. The inner flow, compressed and heated by gravity, produces brighter emission at higher characteristic frequencies. The outer flow is cooler, slower, and produces emission at lower frequencies. The observed spectrum at any given moment is an integral over all contributing radii, filtered by the optical depth at each frequency. Now we introduce the feature that makes black holes imageable in a genuinely new way. Strong gravitational lensing creates a shadow in the apparent brightness distribution, a dark depression against the glowing background of the accretion flow. The shadow is not the event horizon itself, but the lensed imprint of the event horizon's influence on photon trajectories. It arises because the black hole's gravity captures photons that would otherwise reach the observer, removing them from the image and creating a brightness deficit at the center. The shadow is surrounded by a brighter ring, where lensing concentrates photons from a wide range of emission directions into a narrow annular feature. The shadow size is a robust geometric prediction of general relativity. It depends on the black hole's mass and distance, both of which are known for Sagittarius A, and on the spin and inclination angle, which affect the shape of the shadow, but only modestly for realistic parameters. The shadow is larger than the event horizon itself as seen from far away, because lensing enlarges the effective cross-section for photon capture. Photons that would miss the event horizon in flat spacetime can be bent inward and captured by the curved geometry of the near-horizon environment. The photon ring surrounding the shadow is formed by photons that pass close to unstable circular orbits before escaping toward the observer. These near-circular trajectories allow photons to orbit the black hole once, twice, or many times before their eventual fate is determined. Each additional loop adds delay and brings the photon closer to the shadow boundary. In an idealized calculation with a static, geometrically perfect setup, these multiple orbits would create a series of extremely thin, nested rings. In the real universe, plasma emits from a range of radii, and the ring is broadened and made asymmetric by the combination of lensing, Doppler beaming from the rotating plasma, and the irregular brightness distribution of the accretion flow. The shadow and ring depend primarily on mass, spin, and viewing angle, and they are far less sensitive to the messy details of plasma turbulence than are the detailed brightness patterns in the accretion flow. This robust insensitivity to plasma details is what makes horizon-scale imaging so powerful as a test of general relativity. The geometry is set by the spacetime, not by the plasma, so deviations from the predicted shadow size or shape carry information about the gravitational theory itself, rather than about the particular state of the magnetized plasma at the time of observation. Polarization provides a second, independent channel of information that brightness measurements alone cannot supply. Synchrotron emission is intrinsically polarized when the magnetic field has an ordered component. The polarization fraction and angle encode the projected magnetic field geometry in the emitting region. They also encode the effects of relativistic transport on the polarization vector itself, because light propagating through curved spacetime undergoes a rotation of its polarization plane that has no analog in flat space. Between the emitting region and the observer, polarized light passes through magnetized plasma that causes Faraday rotation, a wavelength-dependent twisting of the polarization angle. Faraday rotation depends on the electron density and magnetic field strength integrated along the line of sight. It scales strongly with the square of the wavelength, making it a much more severe effect at longer radio wavelengths than at infrared or millimeter wavelengths. Measuring and modeling Faraday rotation provides constraints on the density and magnetic field in the intervening plasma, including the accretion flow itself, and separating Faraday effects from intrinsic polarization variability is a critical and challenging step in interpreting the data. The Event Horizon Telescope achieves micro-arcsecond resolution by linking radio dishes across Earth into a virtual aperture using the technique of very long baseline interferometry. The resolution is determined by the longest baseline, and continent-spanning baselines provide enough resolution to probe structures at the scale of the black hole shadow predicted for Sagittarius A. The technique is powerful but fragile in specific ways. Each pair of telescopes measures a single spatial frequency of the source's brightness distribution. A Fourier component corresponding to the fringe pattern their baseline would produce for a point source. Assembling these Fourier samples into an image requires reconstruction algorithms that must fill in the spatial frequencies not sampled by the array, and different algorithms can make different assumptions about what the source looks like in the gaps. For Sagittarius A, the reconstruction challenge is compounded by the source's variability. The source evolves during the observing night, so the data accumulated over several hours are not consistent with a single static image. Early in the observation, the source may be bright on one side of the ring. Hours later, the bright region may have shifted. The final synthesis image then reflects some time average of the evolving source, and bright features in that average may not correspond to any structure that actually existed at a single moment. The baseline expectation, built from the combination of general relativistic geometry and plasma physics, predicts a shadow consistent with the measured mass, a ring of lensed emission that is asymmetric due to Doppler beaming, stochastic brightness fluctuations from turbulence, and polarization patterns that encode the magnetic field geometry filtered through Faraday effects. The anomaly, whatever it ultimately represents, must deviate from this baseline in ways that survive the observational filtering imposed by sparse sampling, atmospheric noise, calibration uncertainties, and the variable source structure. What the investigation ultimately asks is whether the deviations are real, whether they repeat across independent datasets and methods, and whether they point toward a physical cause within the known landscape of plasma physics and strong gravity, or whether they demand something genuinely. That question is where the real journey begins, and it starts not with speculation but with the hardest work in modern astrophysics: the careful, systematic separation of signal from noise at the edge of what instruments can measure, in the most extreme gravitational environment our galaxy provides. The baseline is established. The anomaly has been introduced. The investigation can now follow the data wherever it leads, with rigor as its compass and the galactic center as its inexhaustible laboratory. What remains is to understand, step by step and measurement by measurement, what Sagittarius A is actually doing in the dark. With the baseline established and the anomaly introduced, the investigation shifts from what should happen to what the instruments actually recorded. Theory is a map, but the territory is written in data, and data collected at the edge of instrumental capability from a source that refuses to hold still while being observed is a territory full of ambiguity, surprise, and the constant risk of mistaking the map for the terrain. The galactic center does not cooperate with clean experimental design. It is not a laboratory where variables can be controlled one at a time. It is a crime scene where the evidence was collected under difficult conditions by multiple independent teams who did not always agree on what they found, and where the most important clues may be hiding in the noise that surrounds the signal. The first data stream that demands examination is the light curve. Brightness plotted against time, it looks deceptively simple when displayed on a screen. A baseline level of emission persists, fluctuating gently, and then spikes appear, sharp rises in brightness that stand above the background before decaying back toward quiescence. The baseline itself is not flat. It wanders up and down on all timescales simultaneously, which is the hallmark of a process with what statisticians call red noise character, more power at longer timescales, a kind of variability that has memory without having a clock. Above that wandering baseline, the flares rise and fall, and the question becomes immediate and pressing. Are the flares distributed randomly in time, consistent with a turbulent process that produces bursts whenever conditions happen to them? Or do they show a clustering, a preferred spacing, a tendency to repeat at a cadence that encodes a physical timescale in the inner accretion flow? Answering that question requires more data than any single observing campaign can provide, because short datasets are especially vulnerable to false periodicities. A random process can produce a convincing-looking pattern in a limited sample simply because randomness does not enforce uniformity. 3 flares separated by similar intervals can appear by chance from a completely memoryless process. 10 flares showing similar separation is harder to explain by chance. 20 flares across multiple independent campaigns showing a consistent preferred spacing is very difficult to dismiss. The challenge is that 20 well-sampled flares from the galactic center require years of coordinated observations across multiple facilities, and the cadence is never perfectly uniform because weather, scheduling, and competing scientific priorities create gaps that can manufacture or destroy apparent patterns depending on where they fall. The near-infrared provides the sharpest access to this timing question because flares in this band are dramatic, rising sharply above a relatively stable background, and because infrared detectors can achieve the subminute cadence needed to resolve the inner timescales. The gravity instrument transforms this capability by adding astrometric information to the brightness measurement. Instead of just recording how bright the source is at each moment, gravity records where the brightness is centered on the sky, and it does so with a precision that translates into sensitivity to motion at scales comparable to the black hole's gravitational radius. This is an extraordinary capability because it means that during a flare, we can track not just the total brightness, but the apparent position of the emitting region as it evolves. If the emitting region is moving, orbiting, or if multiple lensed images are trading dominance, the centroid will trace a path on the sky that encodes that motion. The centroid measurements during bright infrared flares reveal something striking. In several well-documented events, the brightness centroid traces a path that is not random and not stationary. It moves. The motion has a preferred sense of rotation and a spatial scale that is consistent with orbiting near the innermost stable circular orbit. The path is not a perfect circle because turbulence, differential rotation, and lensing all distort the simple picture of a compact, bright region orbiting on a fixed track. But it is coherent enough, persistent enough over the duration of individual flares, and consistent enough across independent events to be taken seriously as a physical signature rather than an instrumental artifact. The orbital interpretation is straightforward in its outline, if not in its details. A compact, bright region, a hotspot created by magnetic reconnection or by a local compression of the plasma, forms near the innermost stable circular orbit. It orbits the black hole with a period set by the orbital dynamics at that radius. As it orbits, the combination of Doppler beaming and gravitational lensing modulates its apparent brightness, brightening the approaching side and dimming the receding side. The centroid of the total emission tracks the orbital motion, moving in a loop that reflects the hotspot's path around the black hole projected onto the plane of the sky. The period of that orbit, for a mass of 4 million solar masses, works out to roughly 17 to 30 minutes depending on the orbital radius and the black hole's spin. This is a human timescale, which is part of what makes the galactic center so immediately compelling as a laboratory. We are watching something orbit the nearest supermassive black hole in real time, on timescales short enough to track within a single observing session. The flare brightens, the centroid begins to move, the motion traces a partial arc over the course of an hour, and then the flare fades as the hotspot dissipates. In the best documented events, the arc is clear enough that its properties can be compared with theoretical predictions in detail, but the detail is where the complications begin. In a simple hotspot model, the centroid path should have a specific shape determined by the inclination of the orbit relative to our line of sight, the eccentricity of the orbit, and the lensing geometry set by the black hole's mass and spin. The path should be an ellipse projected on the sky, with the shape and orientation of the ellipse encoding the orbital parameters. When the observed centroid tracks are compared with these theoretical predictions, the match is encouraging but imperfect. The general character of the motion fits the orbiting hotspot picture. The spatial scale is right, the sense of rotation is consistent across events. But the specific shape of the tracks and the relationship between the centroid position and the flare brightness do not always follow the detailed predictions of the simplest models. Some tracks show apparent motion that is faster than a simple circular orbit at the expected radius would produce. Others show the centroid jumping discontinuously rather than moving smoothly, as if the dominant lensed image suddenly switches from one path to another. Still others show the centroid moving in the right general direction, but at the wrong rate, suggesting that the emitting region may be at a different radius than the simple model assumes, or that lensing is playing a more complex role than the first-order calculation captures. These imperfections could reflect genuine complexity in the plasma, such as a hotspot that is not compact but extended, or one that is shearing and evolving as it orbits. They could reflect the superposition of multiple hotspots created by a single reconnection event. They could reflect the effect of higher-order lensed images that contribute to the total centroid in ways that are hard to disentangle from the primary image. Or they could indicate that the black hole's spin and orientation relative to our line of sight are different from the values assumed in the comparison models, because spin affects the shape of the photon orbit and the location of the innermost stable circular orbit in ways that change the predicted centroid track. The investigation cannot rest on centroid astrometry alone, because each of these alternative explanations predicts different behavior in other observables. If the centroid tracks reflect genuine orbital motion of a compact hotspot, then the polarization should rotate coherently during the same events, because the hotspot carries a magnetic field that appears at different projected angles as the hotspot moves around the orbit. If the tracks reflect lensing switching between images, then the spectral properties should remain roughly constant during the apparent jumps in position, because the same plasma is being viewed through a different geometric path. If the tracks reflect extended shearing emission, the polarization fraction should decrease as the coherent field in the compact source is diluted by the varying field directions in the stretched arc. Polarization data from the same flares provide exactly the kind of independent constraint needed to distinguish these scenarios. During infrared flares, the polarization fraction rises above the quiescent baseline, and the polarization angle evolves during the flare. The rise in polarization fraction is consistent with the emitting region briefly hosting a more ordered magnetic field than the surrounding turbulent plasma, which is expected if a reconnection event has organized the local field before turbulence can shred it again. The evolution of the polarization angle during the flare is more diagnostic. In several well-observed events, the polarization angle rotates during the flare in a way that is correlated with the centroid motion. As the centroid moves around its apparent arc, the polarization angle changes by tens of degrees in a direction, and at a rate that is consistent with the projected magnetic field direction changing as an orbiting hotspot moves around the black hole. This correlation between position and polarization is a strong argument for genuine physical orbital motion, because a purely geometric effect like lensing switching between images would not naturally produce the same correlation. The correlation is not perfect, and there are events where the polarization behavior is harder to interpret cleanly, but the overall pattern across well-documented flares supports the picture of a physically moving, magnetically coherent emitting region. The rotation of the polarization angle also encodes information about the magnetic field topology that goes beyond the simple orbiting hotspot picture. If the hotspot moves through a magnetic field that has a preferred large-scale orientation, such as a toroidal field wrapping around the accretion flow, or a vertical field threading the inner region, then the polarization angle should not simply trace the projected direction of a locally radial or toroidal field. Instead, it should reflect the combination of the local field geometry and the global topology that the hotspot samples as it orbits. A toroidal dominant field would produce a polarization angle rotation that goes through a full 360 degrees during one complete orbit. A radial dominant field would produce a different rotation pattern. A tilted or disordered field would produce an irregular pattern that does not complete a smooth rotation. The observed rotations are large, sometimes exceeding 100 degrees during a single flare that corresponds to a fraction of a complete orbit. This implies either that the field is nearly uniform, and the hotspot is sampling a large fraction of the field's orientation range during the flare, or that the field itself is rotating or evolving during the flare on timescales comparable to the orbital period. Both possibilities are physically motivated. An orbiting hotspot moving through a toroidal field would naturally produce a large rotation if the orbit is nearly face-on, so that the hotspot covers a large projected angle quickly. A reconnection event that reorganizes the local field while the hotspot orbits would also produce a rapid rotation, though in this case the rotation would not necessarily correlate smoothly with the centroid motion. Distinguishing between these scenarios requires measuring the Faraday rotation along the line of sight during the flares and verifying that changes in the observed angle reflect changes at the source rather than changes in the intervening magnetized plasma. At infrared wavelengths, Faraday rotation is negligible, which means that rapid angle changes in the infrared are almost certainly intrinsic to the emitting region rather than imposed by the line of sight. This is a significant advantage of infrared polarimetry over polarimetry at longer wavelengths where Faraday effects are severe. The X-ray connection adds a third layer of constraint. During the brightest infrared flares, X-ray telescopes often detect simultaneous brightening at high energies. The correlation between infrared and X-ray flares is not perfect. Many infrared flares have no detected X-ray counterpart, and the ratio of X-ray to infrared brightness varies substantially between events. But when both are present simultaneously, they constrain the electron energy distribution and the emission mechanism in ways that neither band can achieve alone. The simplest interpretation of simultaneous infrared and X-ray flares from the same region is that a single population of electrons, accelerated to a broad range of energies by magnetic reconnection, produces synchrotron emission at infrared wavelengths from the higher energy electrons and either synchrotron or inverse Compton emission at X-ray wavelengths from the most energetic electrons. The infrared and X-ray luminosities together constrain the peak electron energy and the magnetic field strength. The timing relationship between the two bands constrains the geometry of the emitting region, because if inverse Compton is responsible for the X-rays, the seed photons must overlap spatially with the accelerating electrons, setting a constraint on the emitting region size. When flares show the timing structure associated with the anomaly but lack X-ray counterparts, the interpretation becomes more constrained. A purely geometric effect, such as lensing magnification of a region that is simply orbiting without additional particle acceleration, would not be expected to produce strong X-ray emission because the electron energy distribution would not be enhanced. Doppler beaming makes the approaching side of the orbit brighter in all bands equally, including X-rays. But if the X-ray band requires the most energetic electrons, and those electrons are not being freshly accelerated, the X-ray brightening from Doppler beaming alone might fall below the detection threshold, while the infrared brightening remains detectable. This provides a potential explanation for the X-ray quiet events, but it also creates a testable prediction. If geometric effects like lensing and Doppler beaming are responsible for the timing structure without additional particle acceleration, then the flare spectrum during the quasi-periodic events should be softer than during the brightest flares that do have X-ray counterparts. The spectral index should reflect a cooling electron distribution rather than a freshly heated one. Whether this prediction is borne out by the existing data is a question that requires careful spectral analysis of individual flares classified by their multiband behavior, and that analysis is ongoing. The Event Horizon Telescope data introduce a qualitatively different kind of evidence. Rather than tracking brightness or position from a single telescope or a small interferometric array, the EHT synthesizes a planet-scale aperture from stations scattered across multiple continents. The result is sensitivity to structures at the scale of tens of microarcseconds, resolving the predicted shadow of Sagittarius A for the first time. The image published by the EHT collaboration shows a ring-like structure with a central brightness depression, consistent with the shadow predicted by general relativity for a 4 million solar mass black hole at the distance of the galactic center. The agreement between the observed ring size and the predicted shadow size is remarkable. The ring diameter extracted from the EHT images is consistent with the mass measured from stellar orbits, confirming that the same gravitational influence that governs the orbits of stars at distances of thousands of gravitational radii also controls the geometry of photon trajectories at a few gravitational radii. This cross-validation between stellar dynamics and horizon-scale imaging is one of the strongest confirmations of the black hole interpretation for Sagittarius A ever achieved, because it links two entirely independent measurement techniques that probe radically different physical scales. But within that success, the anomaly appears as a specific pattern in the image reconstruction that goes beyond simple ring shadow geometry. Different reconstruction algorithms applied to the same EHT dataset converge on a ring with the correct diameter and a central depression with the expected depth, but they disagree on the detailed brightness distribution around the ring. The disagreements are expected at some level because the algorithms make different assumptions about what the source looks like in the spatial frequencies not sampled by the array, and because variability during the observation means that different time windows within the dataset contain different source states. What is unexpected is that certain specific features in the brightness distribution show more consistency across algorithms than expected for purely random turbulent emission. In particular, the angular position of the brightest point along the ring shows a preference for certain orientations across multiple independent reconstructions and across different subsets of the data. This angular preference is not what a completely stochastic accretion flow would predict. A random turbulent flow would produce a brightness distribution that evolves continuously through all possible orientations, and its time average should not strongly prefer any particular direction. The observation of a preferred orientation hints at either a persistent asymmetry in the accretion flow, such as a preferred angular momentum axis, or a large-scale magnetic field with a preferred orientation, or at an effect of the black hole's spin that organizes the emission asymmetrically through frame dragging. The closure phase is the EHT observable most sensitive to asymmetric structure in the source brightness distribution. Closure phase is constructed from the interferometric phases measured on three baselines that form a triangle, and it is immune to the station-based phase errors that dominate single baseline measurements. A perfectly symmetric brightness distribution produces a closure phase of 0, while any asymmetry produces a non-zero closure phase whose value and sign encode the nature of the asymmetry. The EHT data for Sagittarius A show closure phases that are inconsistent with 0, confirming that the brightness distribution is asymmetric, as expected from the combination of Doppler beaming and lensing. The question is whether the specific values of the closure phases and their evolution during the observation are consistent with the predictions of general relativistic magnetohydrodynamic simulations, or whether they deviate in ways that require modifications. When the EHT closure phases are compared with synthetic observations generated from GRMHD simulations, the match is generally good but not perfect. The simulations span a wide range of parameters, including different spin values, different magnetic field configurations, and different electron heating prescriptions. The observed closure phases fall within the range spanned by the ensemble of simulations, which means they do not definitively rule out any particular model. But they also show a tendency to cluster in a region of closure phase space that is more consistent with strongly magnetized, magnetically arrested disk simulations than with weakly magnetized standard and normal evolution simulations. This preference is not definitive because the simulation ensemble is large and because the observational uncertainties are significant. But it is suggestive because magnetically arrested disks are precisely the configurations that might be expected to produce the kind of organized, persistent magnetic structure that the anomaly hints at. The time evolution of the closure phases during an EHT observing night reveals something additional. For Sagittarius A*, unlike for M87*, the closure phases change measurably during the observation. This change reflects the source variability that makes Sagittarius A such a challenging target, but the pattern of change is not entirely random. In some observing windows, the closure phase evolves smoothly and then returns toward its earlier value, as if the source is exploring a limited region of its accessible brightness configurations rather than drifting freely through all possible states. This constrained evolution would be more consistent with an accretion flow organized by a strong magnetic field that limits how far the brightness distribution can deviate from a preferred configuration. Interpreting this behavior requires comparing it with the statistical properties of simulated light curves from GRMHD models. If the real source spends more time near certain brightness configurations than the simulations predict, it suggests that the real physical process includes a stabilizing mechanism not captured by the simulations. Possibilities include kinetic effects that the fluid simulations cannot represent, magnetic flux that is more coherent than what the simulations typically produce, or a physical boundary condition at the inner edge of the flow that keeps the brightness distribution closer to a preferred state. Each of these possibilities connects to the broader question of what controls the accretion flow's magnetic state near the horizon. The interstellar medium between Earth and the galactic center is itself a source of complications that must be quantified carefully before any claim about the source can be trusted. Radio waves traveling from Sagittarius A to Earth pass through ionized gas in the galactic disk, whose density fluctuates on scales from thousands of light-years down to microscopic. These density fluctuations scatter radio waves through a process analogous to the twinkling of stars in Earth's atmosphere, but operating over a much longer path and producing effects that are far more severe at lower radio frequencies. Scattering broadens the apparent size of the source by blurring it, with the degree of blurring scaling as the square of the wavelength. At centimeter wavelengths, scattering dominates the apparent image size of Sagittarius A to the point where the intrinsic structure is completely hidden beneath a smooth, frequency-dependent blur. At millimeter wavelengths used by the EHT, scattering is reduced to a level where it can be modeled and partially corrected, but it is not negligible. The scattering kernel for Sagittarius A has been characterized using observations at multiple frequencies, and the residual scattering at EHT frequencies is included in the systematic error budget for image reconstructions. Beyond simple blurring, scattering can introduce refractive substructure into the apparent image of a compact source. Refractive scattering occurs on larger spatial scales than diffractive scattering, and it creates brightness fluctuations that can masquerade as real source structure. A spatially incoherent extended source like the accretion flow around Sagittarius A is less affected by refractive scattering than a point source would be, but the inner ring structure, which is effectively compact on scales smaller than the scattering kernel, can show refractive modulations that change with time as the scattering screen moves relative to the line of sight. Characterizing refractive scattering requires measuring the statistics of apparent size and brightness fluctuations at multiple frequencies and comparing them with theoretical models of the scattering screen. The current best models of the Sagittarius A* scattering screen predict refractive noise levels that are smaller than the anomaly signals being discussed, which provides some confidence that the anomaly is not primarily a scattering artifact. But the models have uncertainties, because the scattering screen is not perfectly characterized, and because the three-dimensional distribution of scattering material along the line of sight is not known in detail. The possibility that the scattering screen contributes to or modulates the anomaly cannot be entirely excluded. Faraday rotation provides an independent constraint on the line-of-sight medium. The rotation measure toward Sagittarius A is among the highest measured toward any galactic source, implying a large product of electron density and magnetic field along the line of sight, integrated over a path that includes both the accretion flow and the interstellar medium. The rotation measure itself is variable, changing on timescales of days to months, which implies that the magnetized plasma contributing to the rotation is itself time variable and is probably located at or near the galactic center rather than distributed uniformly along the line of sight. The large rotation measure means that at centimeter wavelengths, the polarization angle undergoes many complete rotations within a single observing bandwidth, effectively depolarizing the signal through bandwidth depolarization. At millimeter wavelengths, the rotation is small enough that this effect is manageable, and the intrinsic polarization of the source can be measured with appropriate calibration. At infrared wavelengths, Faraday rotation is entirely negligible, which is why infrared polarimetry provides the cleanest access to the intrinsic magnetic field geometry of the emitting region. The variability of the rotation measure is itself informative about the accretion physics. Theoretical models of the accretion flow predict a rotation measure that depends on the density and magnetic field in the outer portions of the flow, where the medium is still transparent at the observed frequency. Comparing the measured rotation measure with model predictions constrains the accretion rate and the radial profile of the magnetic field. The current constraints from rotation measurements suggest an accretion rate at the outer boundary of the flow that is several orders of magnitude higher than what actually crosses the horizon, implying that most of the inflowing gas is turned around by some combination of pressure-driven winds and magnetically driven outflows before it reaches the black hole. This picture is consistent with the low luminosity of Sagittarius A and provides a self-consistent account of where the missing energy goes. Statistical rigor is the gatekeeper through which every claim about the anomaly must pass before it can be taken seriously as a physical discovery rather than a measurement artifact. The history of astronomy includes many examples of apparent periodicities in variable sources that turned out to be statistical flukes rather than physical signals. Red noise processes, which describe systems with more variability power at longer timescales, are particularly prone to producing false periodicities because rare alignments of random fluctuations can look exactly like a repeating signal to the human eye, and even to automated detection algorithms that are not properly calibrated against realistic noise models. The standard approach to testing for quasi-periodic signals in noisy time series data begins with characterizing the noise itself. For a variable source like Sagittarius A, the noise is not white, with equal power at all frequencies. It is red, with a power spectrum that rises toward lower frequencies following a power law. Fitting that power law to the data requires a range of timescales that is typically longer than the signal timescale of interest, and the data from any single observing campaign may not cover a sufficient range to determine the power law slope reliably. Errors in the noise model translate directly into errors in the significance estimate for any detected signal. Given a noise model, the significance of a quasi-periodic signal can be estimated by generating large numbers of synthetic time series with the same statistical properties as the noise, then computing the power spectrum or other detection statistic for each synthetic series and determining what fraction of them produces a peak as strong as the observed one. If fewer than 1% of the synthetic series match the observed peak, the signal is described as significant at the 1% level, or equivalently, would occur by chance roughly once in every 100 similar observations. Whether that threshold is sufficient to claim a discovery depends on the number of independent searches conducted, because searching many frequency bins or many datasets inflates the number of opportunities for a false detection. For the anomaly in Sagittarius A, multiple teams have applied variants of this analysis to infrared, X-ray, and millimeter light curves and centroid tracks. The results are not uniform. Some analyses find that the quasi-periodic signal is significant at a level that would conventionally be described as interesting but not definitive, typically a few sigma above the expected noise level. Other analyses, using different noise models or different statistical tests, find significance that is reduced but not eliminated when the trial's factor is properly accounted for. The disagreements reflect genuine methodological differences rather than errors, because the choice of noise model, the choice of detection statistic, and the choice of time window all affect the result. What distinguishes the anomaly from many previous claims of quasi-periodicity in Sagittarius A is its recurrence across independent datasets and across different observable quantities. A signal that appears only in one light curve from one night could be a chance fluctuation. A signal that appears in centroid tracks, in polarization rotation, and in EHT closure phases from different observing campaigns is much harder to explain as coincidence, because the datasets are independent and the detection methods are different. The probability that all of these independent analyses would find consistent signals by chance is much smaller than the probability that any one of them would. This is the logic of triangulation applied to the anomaly. No single line of evidence is definitive. Each line has its own uncertainties and potential biases. But when multiple independent lines point to the same physical feature at the same spatial scale and the same characteristic timescale, the collective weight of evidence exceeds what any individual component could achieve. The anomaly's strength comes not from a single dramatic detection, but from a pattern of concordance across methods, instruments, and epochs that is difficult to manufacture by coincidence. The difficulty is that concordance is also difficult to evaluate rigorously when the analysis pipelines share assumptions. If all the analyses assume the same noise model, for example, and that noise model is wrong, then all of them could be biased in the same direction. If all the analyses define the signal using the same timescale range, they are more likely to find agreement than if they independently derived the preferred timescale from first principles. Evaluating these shared assumptions requires either independent theoretical predictions for the preferred timescale, such as the orbital period at the innermost stable circular orbit for the measured black hole mass, or independent observational constraints that come from entirely different physics. Theoretical prediction for the preferred timescale is one of the strongest arguments that the anomaly is not purely statistical. The observed quasi-period of the centroid tracks and flare timing structure, roughly 20 to 30 minutes in the best documented events, falls in the range predicted for orbital motion near the innermost stable circular orbit for a 4 million solar mass black hole with moderate spin. This is not a prediction that was made after the fact to match the data. The orbital period at the ISCO was calculable from the black hole's mass before the anomaly was identified, and the agreement between the predicted and observed timescales provides an independent check that is not subject to the same statistical concerns as the significance estimate. The orbital period at the ISCO depends on the black hole's spin. For a non-spinning black hole, the ISCO is at 6 gravitational radii, and the orbital period for Sagittarius A S mass is approximately 28 minutes. For a maximally spinning black hole, the ISCO for prograde orbits moves inward to 1 gravitational radius, and the orbital period decreases to a few minutes. For retrograde orbits around a maximally spinning black hole, the ISCO moves outward and the period increases. The fact that the observed quasi-period is consistent with the non-spinning or moderately spinning case is itself information about the spin, though the uncertainty in the period measurement and the possibility that the emission comes from a range of radii, rather than exactly, the ISCO make it difficult to derive a precise spin constraint from this measurement alone. The investigation must also confront the possibility that the anomaly is not a signal from the vicinity of the event horizon at all, but rather a manifestation of known physical processes operating at larger radii in the accretion flow. The galactic center environment includes many potential sources of quasi-periodic variability at timescales from minutes to years. Orbiting gas clumps, spiral density waves, and magnetic flux tubes at large radii could all produce periodic modulations in the accretion rate that propagate inward and manifest as brightness variability. Tidal disruption of asteroids and smaller bodies passing close to the black hole could inject quasi-periodic bursts of material. Resonances between orbital frequencies at different radii could create beat periods that appear to repeat without corresponding to the orbital period of any single structure. Distinguishing between a near-horizon origin and a more extended origin for the quasi-periodic signal requires information about the spatial scale of the emitting region. If the signal comes from near the ISCO, then the total emission region is small, spanning only a few gravitational radii. The light travel time across this region is minutes, consistent with the observed rise times of the associated flares. The synchrotron cooling time for the emitting electrons in a magnetic field of typical strength is also minutes to tens of minutes, consistent with the observed flare durations. If the signal came from much larger radii, the relevant timescales would be different, and the spatial extent of the emitting region would be resolvable with gravity. The gravity astrometric data provide the most direct spatial constraint on the emitting region. The centroid tracks during the quasi-periodic flares span a spatial scale of tens to a few tens of microarcseconds, corresponding to physical distances of a few tens of gravitational radii at the distance of Sagittarius. This scale is consistent with emission from near the ISCO and inconsistent with a much more extended emitting region. The loops traced by the centroid are too small to be produced by orbiting structures at large radii, where the projected orbital scale would be much larger, and the orbital period would be much longer than the observed quasi-period. The spatial scale of the centroid motion is also consistent with the scale over which gravitational lensing effects are important. At a few gravitational radii, the photon orbit and the higher-order lensed images are confined to a region whose angular scale matches the observed centroid excursions. This consistency supports the interpretation that lensing is playing an important role in shaping the centroid tracks, which in turn supports the near-horizon interpretation of the emission. If the emitting region is confirmed to be near the horizon, then several additional predictions can be tested. The orbital velocity at the ISCO is a significant fraction of the speed of light, roughly half the speed of light for a non-spinning black hole in the prograde sense. At these velocities, special relativistic effects are important. Doppler beaming is not a small correction but a dominant modulation, brightening the approaching side of the orbit by a large factor and dimming the receding side. The amplitude of the flux modulation associated with the quasi-periodic centroid motion should reflect this beaming, with brightness peaks coinciding with phases of maximum approach velocity. In several well-documented events, the timing relationship between flux peaks and centroid position is consistent with Doppler beaming from an orbiting hotspot. The brightest phases tend to occur when the centroid is displaced in the direction consistent with the approaching side of an orbit, and the faintest phases occur when the centroid is on the receding side. The amplitude of the flux modulation is also consistent with the expected beaming factor for near-light-speed orbital velocities. These consistencies support the orbiting hotspot picture and reinforce the interpretation that the emission is genuinely coming from near the ISCO, rather than from a more extended region, where velocities would be much lower and beaming would be negligible. The polarization provides a further consistency check. At near-light-speed orbital velocities, the relativistic aberration of light changes the apparent direction of the magnetic field in the emitting region, as seen by the distant observer. This aberration effect rotates the apparent polarization angle in a way that depends on the orbital phase, adding a systematic swing that is superimposed on whatever intrinsic rotation the magnetic field geometry produces. In the best documented events, the total polarization angle swing during a flare is consistent with the combination of relativistic aberration and the expected rotation of the projected magnetic field direction as the hotspot orbits. Separating these two contributions requires modeling that accounts for both the orbital motion and the magnetic field topology, and the results suggest that both are present. The conservative physics of magnetized plasma in strong gravity encompasses an enormous range of phenomena, and before any exotic explanation is entertained, that range must be systematically explored. The exploration takes the form of numerical simulations, which are the modern astronomy's most powerful theoretical tool for understanding environments too extreme for analytical approximation. General relativistic magnetohydrodynamic simulations, which evolve the equations governing magnetized conducting fluid in curved spacetime, have become sophisticated enough to produce synthetic observables that can be directly compared with EHT images, gravity centroid tracks, and multi-wavelength light curves. The power of these simulations is that they make quantitative predictions rather than qualitative arguments. A simulation does not just say that magnetic reconnection can produce infrared flares. It predicts the distribution of flare amplitudes, the distribution of flare durations, the power spectrum of the variability, and the polarization properties of the emission. Those predictions can be compared with observations in detail, and discrepancies constrain not just whether the basic picture is correct, but which specific features of the model are responsible for the discrepancies. The simulations consistently reproduce the broad features of Sagittarius A*S observed behavior. They produce variability with the right general statistical properties. They predict ring-like structures in millimeter images with diameters consistent with the observed EHT ring. They produce infrared flares with the right order of magnitude brightness and duration. They predict polarization fractions and rotation measures in the right range. This broad agreement validates the general framework of hot, radiatively inefficient accretion in a strong gravitational field as the correct description of the galactic center environment. The difficulties appear in the details. The simulations tend to underpredict the coherence and repeatability of the anomalous signal. In a long GRMHD simulation run, quasi-periodic signals do appear spontaneously from the turbulent dynamics, but they tend to be short-lived and irregular, with amplitudes and periods that drift substantially from one event to the next. The observed anomaly, while admittedly not perfectly periodic, shows more consistency across events than the simulations naturally produce without special initial conditions or fine-tuned parameters. One source of this discrepancy may be the treatment of electron physics in the simulations. Standard GRMHD simulations track the total plasma energy, but do not follow electrons separately from ions, instead using a prescribed prescription to divide the energy between them. The electron temperature, which determines the synchrotron emission spectrum, is therefore an output of a model rather than a first principles calculation. Different electron heating prescriptions produce systematically different emission properties, and some prescriptions are better at producing coherent, bright flares than others. The choice of prescription is constrained by comparison with observations, but not uniquely determined by them, leaving a degree of freedom that can absorb some discrepancies between simulation and observation. The treatment of magnetic reconnection is another source of potential discrepancy. In GRMHD simulations, reconnection occurs at numerical dissipation scales that are determined by the finite grid resolution rather than by the actual plasma microphysics. The reconnection rate in the simulations depends on the numerical resistivity, which is set by computational constraints rather than physical ones. Real reconnection in a relativistic plasma proceeds at a rate determined by kinetic processes at the electron scale, which is many orders of magnitude smaller than the grid scale of any global simulation. The difference in reconnection rates can affect how frequently and how intensely energy is released in the inner accretion flow, potentially explaining why simulations underpredict the coherence of flares. Particle-in-cell simulations, which track individual particles rather than treating the plasma as a fluid, can capture kinetic reconnection physics but are limited to small regions and short timescales by computational constraints. They cannot simulate the global accretion flow, but can simulate the local physics of a reconnecting current sheet embedded in conditions representative of the galactic center environment. The results suggest that relativistic reconnection is faster and produces more non-thermal particles than would be expected from simple estimates, and that the particle distributions generated by reconnection can have hard spectral tails that extend to very high energies. These kinetic results, when incorporated into global simulations through improved prescriptions, tend to produce more energetic flares with harder spectra, bringing the simulated emission properties into better agreement with the observed flare statistics. But even with improved electron physics, the simulations struggle to reproduce the specific polarization behavior during the anomalous events. The smooth, large-amplitude polarization angle rotations seen in some flares require a level of magnetic field coherence that most simulations do not naturally maintain in the inner accretion flow during active flaring. The turbulent reconnection that drives the flares tends to scramble the local magnetic field, reducing the polarization fraction and making the polarization angle irregular rather than smoothly rotating. Reproducing both the flare energy and the polarization coherence simultaneously is a challenge that no current simulation has fully met. This challenge points to a specific physical question. What sustains magnetic field coherence in the inner accretion flow during periods of active energy release? In a magnetically arrested disk configuration, the large-scale field threading the inner region is maintained by the balance between magnetic pressure from the accumulated flux and ram pressure from the infalling plasma. This large-scale field can preserve a preferred orientation even while turbulence operates locally. A hotspot forming in this environment would be threaded by a coherent portion of the large-scale field, and the polarization of its emission would reflect that coherence rather than the local turbulent scrambling. This specific mechanism, turbulent emission anchored to a coherent large-scale field in a magnetically arrested disk, provides a conservative but sophisticated explanation for the anomaly that does not require modifications to general relativity or exotic compact objects. It requires only that the accretion flow near Sagittarius A be in a strongly magnetized state, and that kinetic reconnection, rather than the slower numerical reconnection in current simulations, be responsible for driving the observed flares. Testing this explanation requires both better observations that can constrain the large-scale magnetic field topology and better simulations that can capture kinetic reconnection within a global accretion context. The magnetically arrested disk scenario also makes specific predictions about the multi-wavelength behavior that can be tested. A strongly magnetized inner flow should show a systematically higher millimeter polarization fraction than a weakly magnetized flow, reflecting the greater coherence of the large-scale field. The rotation measure should be more stable on our timescales, because the large-scale field organization reduces the variability of the line-of-sight integral. The infrared polarization fraction during quiescence should be moderate but non-zero, reflecting the persistent large-scale field even in the absence of active flares. And the flare statistics should show a characteristic signature of the magnetic eruption, events that punctuate the magnetically arrested state, with bright flares corresponding to episodes when accumulated magnetic flux is suddenly expelled and redistributed. Comparing these predictions with existing data provides a mixed picture. The millimeter polarization fraction of Sagittarius A is indeed substantial, roughly 20% during some epochs, which is consistent with a strongly magnetized inner flow. The rotation measure shows variability on timescales of days to months, but is more stable on shorter timescales, which is broadly consistent with the magnetically arrested prediction, but also consistent with other magnetic field configurations. The quiescent infrared polarization is detected, but is relatively low, which may reflect internal Faraday depolarization rather than a truly disordered field. The flare statistics show a broad distribution of amplitudes with rare bright events separated by longer quiescent periods, which could be consistent with magnetic eruption events, but is also consistent with simple turbulent variability. None of these comparisons definitively confirms or rules out the magnetically arrested disk scenario for Sagittarius A. The measurements are suggestive, and the scenario is physically well motivated, but the data are not yet precise enough to distinguish the magnetically arrested prediction from those of other strongly magnetized but not arrested configurations. The next generation of measurements, with improved sensitivity and temporal coverage, will be needed to make this distinction clearly. Frame dragging deserves a more careful examination because it provides one of the most elegant conservative explanations for organized variability in the near-horizon environment. When a black hole rotates, it drags spacetime around with it in the direction of rotation. This is not a subtle effect near the horizon, but a dominant feature of the spacetime geometry. The Kerr solution, which describes the spacetime around a rotating black hole, differs from the non-rotating Schwarzschild solution in ways that become increasingly dramatic as the spin parameter approaches its maximum value. Frame dragging manifests observationally in several ways. It shifts the innermost stable circular orbit, moving it inward for prograde orbits relative to the non-spinning case and outward for retrograde orbits. This shift changes the maximum orbital frequency and the minimum timescale for stable periodic variability. It causes the orbits of massive objects to precess, with the orbital plane rotating around the spin axis at a rate that depends on the orbital radius and the spin magnitude. This precession, called lens-Thirring precession, is a well-established prediction of general relativity that has been measured in solar system contexts and in the orbits of stars around Sagittarius A itself, though with limited precision. If the accretion flow near Sagittarius A is misaligned with the black hole's spin axis, frame dragging will cause the inner portion of the flow to precess. The precession of a misaligned accretion disk is called Bardeen-Pedersen precession, and it operates differentially, with the inner disk precessing faster than the outer disk. This differential precession can produce a warp in the disk that propagates outward. In the inner region where precession is fastest, the disk is driven toward alignment with the spin axis. In the outer region where precession is slower, the disk retains more of its original orientation. The transition between aligned and misaligned regions creates a warped structure that can modulate the emission in complex ways. The precession timescale depends on the orbital radius and on the spin parameter. For Sagittarius A, the precession timescale at a few gravitational radii can range from hours to days depending on the spin and the radius. This is longer than the orbital timescale at the same radius by a factor that grows with radius and decreases with spin. If the anomalous quasi-period reflects a precession timescale rather than an orbital timescale, the implied radius and spin would be different from the orbiting hotspot interpretation. Distinguishing between these two interpretations requires measuring whether the quasi-period is stable or whether it drifts in a way consistent with the expected difference between orbital and precession periods. Precessing structure would also produce a different polarization signature from an orbiting hotspot. The polarization angle modulation produced by lens-Thirring precession traces the rotation of the disk warp rather than the orbital motion of a compact feature. The rotation rate would be the precession rate rather than the orbital rate, and the amplitude of the polarization swing would reflect the inclination of the warp rather than the inclination of the orbital plane to the line of sight. In principle, the combination of timing and polarization constraints could distinguish orbital from precessional origins for the quasi-period, but this requires measurements precise enough to resolve the difference in timescale and amplitude. Frame dragging also affects the photon ring. In the Kerr spacetime, the photon orbit is not symmetric. Prograde and retrograde photons orbit at different radii, and the shadow cast by photon capture is not a perfect circle, but a slightly flattened and shifted shape that depends on the spin magnitude and direction relative to the observer. For Sagittarius A, this asymmetry in the shadow is small for realistic spin values and viewing angles, making it difficult to measure with current EHT precision. But the asymmetry in the brightness distribution around the ring is larger, because Doppler beaming of the rotating plasma creates a persistent brightness asymmetry between the approaching and receding sides of the orbit that grows with spin. Measuring this brightness asymmetry precisely enough to constrain the spin requires images with sufficient dynamic range to distinguish the brighter side of the ring from the fainter side at the level predicted by beaming. The current EHT images show an asymmetric ring with a preferred bright region, consistent with the expected beaming. The angular position of the bright region can be compared with predictions for different spin values and viewing angles to constrain the spin, though the comparison is complicated by the source variability that shifts the bright region during the observation. Future EHT observations with additional stations and improved calibration will improve the dynamic range and temporal resolution of the ring images, allowing more precise spin measurements from the brightness asymmetry. Combined with the spin constraints from the quasi-period of the centroid tracks and the polarization evolution, these measurements could converge on a consistent picture of the black hole's spin that would also constrain the properties of the near-horizon accretion flow. The investigation reaches a natural checkpoint after exhausting the most conservative plasma and strong gravity explanations. The anomaly has been introduced, characterized, and tested against multiple instrumental and astrophysical alternative explanations. It has survived the statistical scrutiny of false periodicity testing, at least at a level sufficient to demand continued attention. It has survived the comparison with simulations well enough to motivate specific improvements in those simulations, particularly in the treatment of electron physics and magnetic reconnection. It has pointed toward a specific regime of accretion physics, the magnetically arrested or strongly magnetized disk, that has additional testable consequences beyond the anomaly itself, but it has not been conclusively explained by any conservative mechanism. The magnetically arrested disk scenario is promising, but the evidence for it is suggestive rather than definitive. The frame dragging and lens thirring explanations are physically well motivated, but require assumptions about the misalignment geometry that are not independently constrained. The kinetic reconnection picture is appealing, but cannot be tested directly with current global simulations. Each conservative explanation captures part of the anomaly, but none captures all of it. This situation is the natural prelude to widening the hypothesis space. Not because the conservative explanations have failed completely, but because they have each failed partially and in ways that are consistent with each other's failures. The combined picture of a strongly magnetized inner flow, possibly in a magnetically arrested state, producing coherent flares through relativistic kinetic reconnection, organized by frame dragging into a quasi-periodic pattern, can account for many features of the anomaly. But the specific repeatability of the pattern, the smooth polarization rotations, and the apparent coherence of the centroid tracks across multiple independent flares remain harder to explain within even this sophisticated conservative picture. The question is whether the gap between the best conservative model and the observations is large enough to motivate genuinely novel physics, or whether it is small enough to be attributed to the known limitations of current simulations and observational methods. That question has no clean answer yet, because both the simulations and the observations are improving rapidly. The next generation of EHT observations, the next generation of infrared interferometry, and the next generation of X-ray timing measurements will all provide additional constraints that will either close the gap or widen it. What is clear is that the anomaly is not going away. It persists across datasets. It is consistent across methods. It falls at the right timescale to be physically meaningful, and it challenges the community to build better models and make better measurements, which is precisely what a good anomaly is supposed to do. The investigation has not reached its conclusion. It has reached the point where the tools available to conventional science are beginning to strain against the precision of the question being asked, and where the possibility of genuinely new physics begins to seem less like speculation and more like a serious scientific option that deserves careful evaluation. That evaluation begins in the next part of this investigation, where the hypothesis space widens to include objects that look like black holes from far away but differ at the edge, and where the question of whether information is truly lost at a horizon moves from philosophical abstraction to observational target. The anomaly that began as a flickering pattern in infrared data has grown into a question about the nature of gravity, time, and the deepest structure of physical reality. Following that question to its conclusion requires following the data to the frontier, where the known and the unknown share a boundary that every measurement is trying to locate more precisely. The investigation continues, and the signal holds its shape against the noise. Something near the horizon of Sagittarius A is keeping a pattern that should not survive. Understanding what that pattern is and what keeps it may be the most important observational project of this generation of astronomers. The conservative explanations have been stretched to their limits. Magnetically arrested disks, frame dragging, kinetic reconnection, and relativistic hotspots have each captured fragments of the anomaly without fully accounting for its persistence, its coherence, or its specific relationship between timing, polarization, and spatial structure. The investigation has not exhausted conventional physics, but it has identified the specific places where conventional physics strains most severely against the data. Those strain points are precisely where the hypothesis space must widen, carefully, and without abandoning the rigor that makes the question worth asking. Widening the hypothesis space does not mean abandoning discipline. It means asking whether there are physical possibilities, permitted by the mathematics we already possess, that have not been adequately tested against the Sagittarius A* data because they were considered too exotic for a source that seemed well described by the standard black hole picture. The history of astrophysics includes many examples of phenomena that were initially explained by exotic hypotheses before better data revealed conventional explanations, but it also includes examples where the conventional explanation was genuinely insufficient and the exotic hypothesis turned out to be correct. Neutron stars were exotic hypotheses before pulsars were discovered. Black holes themselves were exotic hypotheses before stellar dynamics and X-ray binaries confirmed their existence. The lesson is not that exotic hypotheses are always right, but that they deserve careful examination when conventional explanations have been systematically tested and found to be incomplete. The first widening step stays close to conventional general relativity while relaxing an assumption that is often treated as settled. The assumption is that Sagittarius A is precisely described by the Kerr solution, the exact rotating black hole geometry that follows from general relativity's field equations when gravity is the only relevant interaction and the matter distribution is idealized. Real black holes in real astrophysical environments are surrounded by matter, threaded by magnetic fields, and potentially affected by quantum corrections that are not included in the classical Kerr solution. If any of these deviations from the idealized Kerr geometry are large enough to produce measurable effects in the near-horizon region, they could contribute to or modify the anomalous signal. Deviations from Kerr geometry are parameterized in what theorists call bumpy black hole frameworks, or more generally, within the formalism of testing general relativity in the strong field regime. These frameworks add parameters to the Kerr solution that describe possible deviations from the predicted spacetime metric, without committing to any specific alternative theory of gravity. The parameters control how much the spacetime curvature, the location of the photon orbit, and the rate of frame dragging deviate from the Kerr predictions. If the anomaly reflects a specific deviation from Kerr, the parameters describing that deviation can in principle be constrained by the observational data, providing not just evidence for deviation, but a quantitative characterization of what the deviation looks like. The photon ring is particularly sensitive to deviations from Kerr geometry because its radius and shape are determined by the photon orbit, which depends on the near-horizon spacetime curvature. A bumpy black hole with a slightly modified metric would have a photon orbit at a slightly different radius and would cast a shadow of slightly different size. The difference from the Kerr prediction is typically small for perturbative deviations, but it grows for larger deviations and can become detectable with sufficient image precision. The EHT's measurement of the ring diameter already provides constraints on certain types of deviations, ruling out those that would shift the ring size by more than the current measurement uncertainty. The most powerful EHT constraints on metric deviations come from combining the ring diameter measurement with the stellar orbit measurements that constrain the mass and distance independently. If the ring size is measured, and the mass and distance are known from stellar orbits, then any deviation of the ring size from the Kerr prediction for that mass and distance directly constrains the metric parameters. Current data show no significant deviation, but the constraints are still relatively weak for the class of metric deviations most relevant to the anomaly, which are those that primarily affect the near-horizon region while leaving the weak field regime essentially unchanged. This is because stellar orbits probe the gravitational field at distances of hundreds to thousands of gravitational radii, where the difference between Kerr and modified metrics is typically very small. The ring probes much closer to the horizon where deviations are larger, but the ring measurement has its own uncertainties from plasma structure and image reconstruction. Combining these two probes, one from far away and one close in, creates a lever arm that can separate the metric deviation from the plasma effects, but only when both measurements have sufficient precision. Future EHT observations with next-generation arrays will improve the ring diameter measurement to the point where metric deviations at the percent level become testable. At that precision, the question of whether Sagittarius A** S spacetime is exactly Kerr or slightly different becomes an observational question rather than a theoretical one. If a deviation is detected, it could explain the anomaly as a consequence of modified photon orbits that produce slightly different lensing behavior than the Kerr prediction. If no deviation is detected, it tightens the case that the anomaly must be explained by plasma effects rather than spacetime modifications. Beyond parameterized metric deviations, specific alternative theories of gravity make concrete predictions for the near-horizon structure of compact objects. Scalar tensor theories, which add a scalar degree of freedom to general relativity, can produce black holes that carry scalar charge in addition to mass and spin. The scalar charge modifies the spacetime metric in a way that changes the photon orbit and shadow size, and it can also create oscillating scalar field distributions near the black hole that could modulate the observed emission with a characteristic frequency. If Sagittarius A carries scalar charge, the modulation frequency would be set by the scalar field's oscillation frequency, which depends on the mass of the scalar field particle if the scalar field has mass, or on the boundary conditions at the horizon. Modified gravity theories that include higher-order curvature terms in the gravitational action predict corrections to the Kerr geometry that become important near the horizon where curvature is strongest. These corrections can shift the photon orbit, modify the rate of frame dragging, and create additional stable circular orbits inside the classical ISCO that do not exist in the Kerr geometry. If the anomalous quasi-period reflects an orbit at a radius inside the Kerr ISCO that is stabilized by higher-order curvature corrections, then the period and spatial scale of the anomaly would be distinct from anything the Kerr geometry predicts. Testing these alternative gravity theories against the Sagittarius A data requires making predictions precise enough to be distinguished from the Kerr case, given observational uncertainties. The predictions must also be distinguished from plasma effects, which can produce similar apparent deviations without requiring any modification to gravity. This is the core difficulty. In the near-horizon environment, the plasma and the spacetime interact continuously, and plasma effects can mimic spacetime deviations, while spacetime deviations can be mimicked by plasma effects. Separating them requires observables that are sensitive to one but not the other, which is easier said than done in a system where both are extreme and variable. The polarization of the photon ring offers one such observable. In general relativity, the polarization of light emitted by the accretion flow and observed in the photon ring is affected by the geometry of the photon paths near the orbit, in a specific way that depends only on the spacetime metric and not on the plasma properties at the emission point. This effect, called gravitational Faraday rotation or parallel transport, rotates the polarization angle of photons as they travel along curved geodesics near the photon orbit. Different spacetime metrics predict different amounts of this rotation, providing a probe of the metric that is independent of the plasma emission physics. In practice, measuring this polarization rotation in the photon ring requires resolving the ring with sufficient spatial and polarimetric precision to separate the thin ring component from the broader emission. This is beyond current EHT capabilities, but is a target for next-generation interferometric arrays. The principle is established, however, and it illustrates the general strategy for separating spacetime effects from plasma effects in photon ring observations. The ring carries gravitational information in its geometry and polarization that is encoded during photon transport, not during photon emission, making it a purer probe of the spacetime than the broader emission from the accretion flow. The second and more dramatic widening of the hypothesis space considers objects that are not black holes in the classical sense at all, but that mimic black holes so closely in their observable properties that they are difficult or impossible to distinguish from the outside. These objects are collectively called black hole mimickers or exotic compact objects, and they span a wide theoretical landscape from highly speculative to well-motivated by established physics. The concept of a mimicker is more precisely defined than it might initially appear. For an object to mimic a black hole observationally, it must have the same mass and compactness as the black hole it is imitating. It must capture light and matter at the same rate, producing the same shadow and the same accretion emission, and it must avoid producing any distinguishing signal that would immediately reveal its true nature. The challenge for a mimicker is that these conditions are individually easy to satisfy, but collectively very constraining. A neutron star, for example, has a mass and compactness that makes it a poor mimicker of a supermassive black hole because neutron stars have hard surfaces that emit thermal radiation when matter accretes onto them. That thermal emission would be detectable and would immediately distinguish the neutron star from a black hole. A compact object that is as massive and as compact as Sagittarius A but has a surface, however exotic, faces the same problem. Any accreting material that hits a surface must deposit its kinetic energy as heat, and that heat must eventually be radiated. The radiation would be detectable. The question is how faint that surface radiation could be while remaining physically consistent. If the surface is made of exotic material with very low emissivity, or if the surface is somehow cooled by mechanisms not present in ordinary matter, the radiation could potentially be suppressed below current detection thresholds. But the suppression must be extreme, because the accretion luminosity of Sagittarius A is already very low. A surface whose radiation is even a small fraction of the kinetic energy deposited on it would produce detectable emission at some wavelength, unless the energy is somehow redirected or stored. Boson stars represent a class of exotic compact objects that are physically well-motivated and have been studied in considerable mathematical detail. They are hypothetical compact objects made entirely of bosonic particles held together by gravity against quantum pressure from the bosonic field self-interaction. Unlike neutron stars, which are made of fermionic matter and supported by degeneracy pressure, boson stars have no hard surface in the conventional sense. They are made of a coherent quantum field that extends throughout the object's volume, with a density profile that peaks at the center and decreases smoothly toward the exterior without a sharp boundary. The gravitational field of a sufficiently compact boson star can closely resemble that of a black hole at distances larger than the star's effective radius. A distant observer measuring orbital velocities of stars around a compact boson star would find that the orbits are consistent with a black hole of the same mass. The photon orbits in shadow would also be similar to those of a black hole, though not identical. The differences are at the level of the detailed metric near and inside the photon orbit, where the boson star's gravitational field deviates from the Kerr geometry in ways that depend on the boson mass and the self-coupling parameters. One crucial difference between a boson star and a black hole is that the boson star has no event horizon. Light and matter that fall into a boson star are not inevitably captured forever. They pass through the star, interacting with the bosonic field, and can in principle re-emerge on the other side, though they may be thermalized or scattered in the process. This means that in a boson star, information about infalling matter is not necessarily lost. The matter and its information are stored in the oscillations of the bosonic field inside the star and can potentially be released at later times. For the anomaly in Sagittarius A, the boson star scenario is relevant because the absence of a horizon changes what happens to accreting material. In a black hole, material that crosses the horizon is lost. The horizon is a one-way membrane that swallows everything and returns nothing. In a boson star, material that falls in is absorbed into the star's interior, but remains there, gradually affecting the star's overall state. If the accreted material excites oscillation modes of the boson star, those modes can radiate energy at characteristic frequencies set by the boson star's internal structure. These frequencies are not determined by the orbital dynamics of the accretion flow, but by the boson star's own resonant frequencies, which depend on the boson mass and the star's compactness. If Sagittarius A were a boson star, and if accreting material excited resonant oscillation modes, the resulting radiation at those characteristic frequencies could produce a quasi-periodic signal in the observed emission. The period of the signal would be set by the boson star's internal physics rather than by the orbital period of the accretion flow, and it might be different from the ISCO orbital period in a way that is diagnostically distinguishable with sufficiently precise measurements. However, the characteristic frequencies of sufficiently compact boson stars can be similar to the ISCO orbital frequencies, making the distinction challenging with current observational precision. The shadow size of a boson star is another distinguishing feature. For a compact boson star, the shadow can be smaller than for a Kerr black hole of the same mass, because the absence of a hard event horizon means that photons can penetrate into the star's interior rather than being captured at the photon orbit. The effective capture cross-section is smaller, producing a smaller shadow. The difference in shadow size is small for the most compact boson stars that mimic black holes closely, but it is potentially measurable with next-generation EHT observations that improve the shadow size measurement precision to the percent level. Gravastars, which are gravitational vacuum condensate stars, represent another class of exotic compact object, motivated by the idea that quantum gravitational effects might prevent the formation of a classical event horizon. In the gravastar model, the interior of the compact object is not a black hole singularity surrounded by a horizon, but a region of de Sitter space, characterized by a positive cosmological constant, surrounded by a thin shell of ultrarelativistic matter. The thin shell is located near where the event horizon would be in a classical black hole geometry. This construction avoids the singularity and the horizon while reproducing the exterior gravitational field of a black hole to high precision. The thin shell of a gravastar has specific physical properties. It must satisfy certain conditions at its boundaries to be consistent with the junction conditions of general relativity. These conditions constrain the equation of state of the shell material and the relationship between the shell's radius and its total mass. In practice, the shell must be extremely close to the gravitational radius of the object, within a Planck length in some theoretical constructions, making the gravastar observationally nearly indistinguishable from a black hole for distant observers. The difference from a black hole shows up primarily in the behavior of infalling matter near the shell, which is reflected rather than absorbed, and in the spectrum of oscillation modes that a gravastar can support. The reflection of matter at the gravastar surface has a potential observational consequence. In a black hole, infalling material crosses the horizon and is absorbed. In a gravastar, infalling material hits the shell and a portion of it can be reflected outward. The reflected material carries information about the state of the shell and can potentially produce observable signals that have no counterpart in a black hole scenario. In particular, if matter falls in at a roughly constant rate, and a fraction is reflected at each encounter with the shell, the reflected fraction can produce an echo of the info signal that arrives at the observer after a time delay set by the light travel time from the shell to the outer accretion flow and back. These echoes have been discussed in the context of gravitational wave observations of compact object mergers, where they are called gravitational wave echoes. In the electromagnetic domain, the concept translates into reflections of accreting material or electromagnetic radiation from the compact object surface. If Sagittarius A is a gravistar or any object with a reflecting surface near its gravitational radius, then flares in the inner accretion flow might be echoed in the observed emission after a delay determined by the light travel time from the emitting region to the reflector and back. The delay for a surface near the gravitational radius would be on the order of seconds to minutes for Sagittarius A*S mass, which is within the temporal resolution of current observations. The search for echoes in the Sagittarius A light curves is a direct test of the horizon hypothesis. Black holes should produce no echoes because the horizon absorbs everything. A gravistar, or any object with a surface near the gravitational radius, should produce echoes that repeat with a specific time delay and amplitude determined by the reflectivity and location of the surface. The challenge is that echoes would be significantly dimmer than the original flare, because the surface reflectivity is presumably much less than unity, and because the distance to the reflector and back attenuates the signal. Detecting an echo at the expected amplitude against the turbulent accretion flow background requires high signal-to-noise ratio measurements of individual flares with sufficient temporal resolution. Current data from well-observed flares have been searched for echoes with methods analogous to those used in gravitational wave echo searches. The analysis is sensitive to echoes with delays from seconds to tens of minutes and amplitudes down to a few percent of the primary flare brightness. No definitive echo has been detected in existing datasets, but the upper limits on echo amplitude provide constraints on the reflectivity of any potential surface near the gravitational radius. The constraints rule out highly reflective surfaces, but allow surfaces with reflectivity of a few percent or less, leaving a significant range of parameter space unexcluded. Future observations with higher temporal resolution and better sensitivity could either detect an echo, which would be revolutionary, or push the reflectivity constraint below the percent level, which would begin to seriously challenge even the most exotic mimicker scenarios. The information paradox connects the observational anomaly to some of the deepest unsolved problems in theoretical physics. The paradox arises from the combination of two principles that are each well-established individually, but appear to be mutually inconsistent when applied together to black holes. The first principle is quantum mechanics, which states that physical processes are reversible and that information cannot be destroyed. Given a complete description of a physical system at any moment, quantum mechanics in principle allows the complete past and future history of the system to be reconstructed. Information, in this precise sense, is conserved. The second principle is general relativity's description of black holes, which states that matter crossing the event horizon is permanently inaccessible to external observers, and that the black hole's external properties are completely characterized by just mass, spin, and charge. This simplicity is sometimes called the no-hair theorem, because a black hole has no distinguishing features beyond these three quantities. When matter with complex quantum states falls into a black hole, all the detailed information encoded in those quantum states appears to be lost to external observers forever. The black hole's exterior remains characterized only by mass, spin, and charge, regardless of whether the infalling matter was a rock, a book, or a quantum computer. The paradox is sharpest when combined with Hawking radiation. Stephen Hawking showed in the 1970s that quantum field theory in curved spacetime predicts that black holes emit thermal radiation with a spectrum determined entirely by the black hole's temperature, which depends only on its mass and spin. This thermal radiation carries no information about the matter that formed the black hole. As the black hole evaporates through Hawking radiation, it eventually disappears entirely, and the information about the infalling matter is seemingly gone with it, never encoded in any external signal. This is a violation of quantum mechanics because quantum evolution is unitary, which means that the probability of all possible outcomes always adds up to 1, and that the final quantum state is always a unique function of the initial quantum state. Thermal radiation is not unitary because a thermal state does not uniquely encode the state that produced it. Many different initial quantum states could produce the same thermal radiation, so the radiation cannot be used to reconstruct the initial state. If black holes truly produce thermal radiation and truly evaporate completely, then unitarity is violated, and the fundamental framework of quantum mechanics, as we currently understand it, needs modification. Various resolutions to the information paradox have been proposed over the decades, and the debate has intensified rather than diminished as theoretical understanding has deepened. Some proposals involve modifications to the black hole's interior, arguing that information is somehow preserved in the structure of the spacetime inside the horizon and is released in a subtle, non-local way as the black hole evaporates. Other proposals involve modifications to the horizon itself, arguing that the horizon is not a smooth, featureless surface, but has quantum structure that encodes and eventually releases the information. Still others propose modifications to the evaporation process, arguing that the final stages of black hole evaporation are not well described by semi-classical physics and that the information is released in a final burst that does not look thermal. The firewall proposal, introduced by Almary, Marolf, Polchinski, and Sully in 2012, created a particularly sharp version of the paradox. They argued that preserving unitarity while also preserving the equivalence principle, which says that an infalling observer near the horizon should feel nothing unusual, leads to a logical contradiction. Resolving the contradiction within the framework of ordinary quantum field theory appears to require either violating unitarity, violating the equivalence principle, or introducing some dramatic modification of the near-horizon physics. The firewall proposal is that the horizon is surrounded by a region of extremely high energy density, a firewall, that destroys infalling observers rather than allowing them to pass smoothly into the black hole interior. The firewall debate is still unresolved theoretically, but it has concrete observational implications for Sagittarius A, because if a firewall or any similarly energetic structure exists at or near the horizon, it would radiate at a temperature and luminosity that depend on its physical nature. In particular, a firewall at the Planck temperature would radiate at energies far beyond anything we can currently detect from astrophysical sources, but modified near-horizon structures that are less extreme than a Planck temperature firewall might radiate at lower temperatures and lower energies, producing a faint glow that could potentially be detectable in sensitive observations. The connection to the anomaly is speculative but physically motivated. If the near-horizon structure of Sagittarius A is modified by quantum gravitational effects that are weaker than the full firewall scenario, but still more significant than the smooth classical horizon picture, then the modification might leave a signature in the pattern of emitted radiation. The signature would not necessarily be a dramatic departure from the standard accretion spectrum, but could be a subtle modulation that reflects the quantum structure of the near-horizon region. A quasi-periodic pattern, a preferred spatial scale, or a specific polarization, behavior could all in principle reflect quantum near-horizon physics, though distinguishing such effects from plasma effects is extraordinarily challenging. Fuzzballs, which arise from string theory, represent a specific proposal for modifying the near-horizon structure. In string theory, the microstates of a black hole are described not by a smooth spacetime with a horizon, but by complex, extended configurations of strings and branes called fuzzballs. Each microstate is a different fuzzball configuration, and the macroscopic black hole is a statistical average over these microstates. The fuzzball configurations have no horizon and no singularity in the classical sense. Instead, the spacetime ends smoothly at a surface that is at or very near the classical horizon radius, and the string theory degrees of freedom at that surface encode all the information that would have been lost to a classical horizon. Fuzzballs are observationally interesting because the surface where the string theory geometry ends is potentially detectable through reflection effects. Matter falling toward a fuzzball would be reflected at or near the classical horizon radius rather than absorbed, similar to the gravistar scenario. The reflection would produce echoes of infalling signals that could be detected in the electromagnetic emission from the accretion flow. The echo delay for Sagittarius A would be on the same timescale as the ISCO orbital period, which means that fuzzball echoes would be expected at approximately the same timescale as the anomalous quasi-period that has been observed. This coincidence of timescales is suggestive, but must be treated carefully. The ISCO orbital period and the light travel time for a reflection from near the classical horizon radius are both set by the black hole's mass, so they are naturally similar in order of magnitude. The coincidence does not distinguish between a reflection interpretation and an orbital interpretation for the quasi-period without independent information about the amplitude, spectral shape, and phase relationship of the anomalous signal. Nevertheless, the coincidence motivates a careful comparison between the detailed predictions of fuzzball-motivated reflection models and the observed anomaly, because if the two are consistent in detail, the interpretation changes dramatically. The key observable difference between a fuzzball reflection and an orbiting hotspot is the phase relationship between successive peaks. In the orbiting hotspot model, peaks occur at regular intervals set by the orbital period, and the flux modulation has a specific functional form determined by Doppler beaming and lensing. In a reflection model, peaks occur after delays set by the reflection geometry, and the amplitude and spectral shape of each echo depend on the reflectivity and spectral modification imposed by the reflecting surface. If the reflector absorbs certain frequencies preferentially, the echo will have a different spectrum than the primary signal. If the reflector imprints a phase shift, successive echoes will have a specific phase relationship that can be tested by cross-correlating the observed light curve with itself at the relevant lag. The observational strategy for distinguishing black holes from mimickers is now becoming a systematic research program rather than an ad hoc collection of tests. The program is organized around a small number of key observables that are most sensitive to the presence or absence of a horizon and least contaminated by plasma physics uncertainties. Each observable provides an independent constraint, and the combination of constraints from multiple observables is more powerful than any single test alone. The first key observable is the shadow size, which probes the photon orbit and is sensitive to the metric at a few gravitational radii from the object. For a classical black hole, the shadow size is precisely predicted by general relativity given the mass and spin. For a mimicker, the shadow size can differ from the black hole prediction at the percent level, or more depending on the specific model. Current EHT measurements are precise to roughly 10% in shadow diameter, and next-generation arrays are expected to improve this to the percent level. The second key observable is the presence or absence of a photon ring at the precise angular scale predicted by the critical photon orbit. The photon ring is expected to be extremely narrow and bright in the idealized case, but plasma effects broaden it significantly in the real source. Detecting the photon ring as a distinct feature separate from the broader emission requires interferometric baselines longer than those currently available, extending into space. Space-based extensions of the EHT, which are in various stages of proposal and development, would provide the baseline length needed to resolve the photon ring and measure its properties. The third key observable is the echo signature, which directly tests for the absence of a horizon. As discussed, a classical black hole should produce no echoes, while a mimicker with a reflecting surface should produce echoes at a delay and amplitude determined by the surface properties and location. The search for echoes in Sagittarius A emission data is ongoing and will benefit from future observations with higher sensitivity and better temporal resolution. The fourth key observable is the spectral energy distribution in quiescence, when the source is at its lowest detected brightness level. In a classical black hole, the minimum luminosity is set by the irreducible accretion rate and by the radiative efficiency of the flow. In a mimicker with a surface, the minimum luminosity includes the thermal radiation from the surface, which is heated by the accreted matter. The surface temperature depends on the accretion rate and the surface emissivity, and for realistic accretion rates, even a relatively cool surface would radiate detectably above the level expected from a black hole without a surface. Current limits on the quiescent luminosity of Sagittarius A already constrain the surface temperature of any potential mimicker, ruling out high emissivity surfaces with temperatures above a few million Kelvin. Extending these constraints requires deeper observations in quiescence, particularly at millimeter and submillimeter wavelengths, where the expected thermal surface radiation would be brightest for the constrained temperature range. The fifth key observable is the gravitational wave signal from any compact binary that might include Sagittarius A as a component. Gravitational waves from extreme mass ratio inspirals, in which a stellar mass compact object spirals into a supermassive black hole under the emission of gravitational waves, encode detailed information about the spacetime geometry of the central object. The Laser Interferometer Space Antenna, LISA, which is planned for launch in the mid-2030s, will be sensitive to the gravitational waves from extreme mass ratio inspirals in the galactic center. The phasing of the gravitational waveform traces the geodesics of the spacetime, and any deviation from the Kerr metric produces a specific deviation in the waveform phasing that accumulates over many orbital cycles. Extreme mass ratio inspirals are therefore among the most precise tests of the Kerr hypothesis ever envisioned, and galactic center sources within LISA's sensitivity range would provide extraordinary constraints. Whether any extreme mass ratio inspiral sources exist in the galactic center close enough to Sagittarius A to be detectable by LISA within its mission lifetime is uncertain. The rate of inspirals depends on the density of compact objects in the nuclear star cluster and on the dynamics that drive them toward the supermassive black hole. Current estimates suggest that LISA should detect a handful of extreme mass ratio inspirals from the galactic center region during its mission, though predicting whether any specific event will occur during the observing window is not possible. If a detection occurs, it will provide the most precise test, yet of whether Sagittarius A** S spacetime is truly care. The combination of electromagnetic and gravitational wave observations of Sagittarius A over the next decade will constitute the most comprehensive test of the black hole hypothesis ever conducted for any astrophysical source. The electromagnetic observations will probe the accretion flow and the photon ring. The gravitational wave observations will probe the geodesic structure of the spacetime. Comparing the two sets of constraints will allow the separation of plasma effects from geometric effects and will place bounds on metric deviations that no single observational channel could achieve alone. Quantum gravity remains the deepest theoretical framework relevant to the anomaly, even though its effects are expected to be tiny at the macroscopic scales relevant to Sagittarius A. The Planck scale, where quantum gravity effects are naturally important, is at energies and length scales vastly smaller than anything accessible to current or foreseeable instruments. The gravitational radius of Sagittarius A is roughly 10 million kilometers, while the Planck length is approximately 10 to the minus 35 meters. The ratio is approximately 43 orders of magnitude, which seems to eliminate any hope of quantum gravity effects being observable. But this reasoning may not apply uniformly across all aspects of black hole physics. The information paradox suggests that quantum gravity effects cannot be confined entirely to the Planck scale. If information is to be preserved, it must somehow emerge from the black hole during or before evaporation. For a macroscopic black hole like Sagittarius A, Hawking radiation is negligible, and evaporation will not occur on any cosmologically relevant timescale. But the principle that information must be preserved might still have consequences for the structure of the horizon and the near-horizon region, even for black holes that are not evaporating observably. Some theoretical proposals suggest that quantum gravitational corrections accumulate near horizons over time, gradually modifying the near-horizon geometry in ways that become important after the black hole has existed for a sufficiently long time. These corrections are typically called quantum hair, extending the classical no-hair theorem to the quantum realm, where it no longer applies. If Sagittarius A has had its current mass for billions of years, as the galactic center's age implies, then quantum hair might have accumulated to a detectable level, even if the individual quantum corrections are Planck-scale small. This speculative scenario is not well constrained theoretically, but it motivates the search for any systematic deviation from the classical care behavior that grows with the black hole's age rather than with its mass alone. A related idea comes from the holographic principle, which connects the physics of a volume of space to the physics of its bounding surface. In the context of black holes, holography suggests that all the information inside the horizon is encoded on the horizon surface itself, with a density of roughly 1 bit per Planck area. The holographic encoding of information on the horizon might produce observable fluctuations in the near-horizon structure if the encoding process is dynamical rather than static. These fluctuations would be at the Planck scale individually, but their collective effect on the near-horizon spacetime might be amplified by the enormous number of degrees of freedom involved. For a 4 million solar mass black hole, the horizon area contains approximately 10 to the 89th Planck areas, which is an astronomical number of holographic degrees of freedom. Whether the collective quantum fluctuations of that many holographic degrees of freedom can produce macroscopic observable effects is an open theoretical question. Most theoretical estimates suggest that the fluctuations average out over the large number of degrees of freedom, leaving a residual effect that is suppressed by the inverse square root of the number of degrees of freedom. For a macroscopic black hole, this suppression is so severe that the residual effect would be smaller than the Planck length, undetectable by any conceivable instrument. But these estimates rely on assumptions about the statistical behavior of the holographic degrees of freedom that are not derived from first principles. If the degrees of freedom are not statistically independent, if they have long-range correlations imposed by the holographic encoding, then the averaging could be less complete and the residual effect could be larger. The Sagittarius A anomaly does not obviously connect to holographic fluctuations through any specific theoretical mechanism, and claiming such a connection would require a much more developed theoretical framework than currently exists. But the anomaly's existence as an unexplained pattern in the near-horizon emission motivates the development of such frameworks. If theorists can derive a specific prediction for holographic fluctuations at the scale of the current anomaly, it would provide a concrete theoretical target for the observational program to aim at. The dialogue between theory and observation is usually more productive than either discipline working in isolation, and the anomaly is a signal sent from the galactic center to both communities simultaneously. The observational program for the next decade is shaped by the questions that the current anomaly has made specific and testable. The Next Generation Event Horizon Telescope, which is currently in the planning and early development phase, will significantly increase the number of stations in the array, improve the sensitivity at each station, and extend the frequency coverage to higher millimeter and submillimeter wavelengths. These improvements will increase the dynamic range of reconstructed images from the current level of roughly 10 to 1 to potentially hundreds to 1, revealing faint structures in the accretion flow that are currently invisible against the noise. The increased dynamic range will make it possible to detect the photon ring as a distinct component of the millimeter image, separate from the broader emission of the accretion flow. The photon ring's angular scale and brightness profile can then be measured and compared with the general relativity prediction and with modified gravity alternatives. The photon ring is expected to be significantly narrower and potentially somewhat brighter per unit angle than the broader emission, making it distinguishable with sufficient dynamic range even if the current images blur it into the total ring structure. Improved temporal resolution from more sensitive stations and better calibration will allow the EHT to produce time-resolved images of Sagittarius A on timescales of minutes, rather than averaging over an entire observing night. Time-resolved images will directly show the evolution of the brightness asymmetry during flares, allowing the quasi-periodic pattern in the emission to be tracked in the image domain, rather than inferred from visibility statistics. If the brightness distribution shows a systematic motion consistent with an orbiting hotspot, that motion will appear directly in the image sequence rather than being hidden in the closure phase statistics. Space-based extensions of the EHT, using small satellites in Earth orbit or beyond, will provide baselines longer than Earth's diameter and will probe spatial scales smaller than the current resolution limit. These longer baselines will access the innermost photon ring, which is confined to a narrow angular scale smaller than what ground-based arrays can resolve. Detecting the photon ring as a distinct feature will provide the most precise measurement of the near-horizon spacetime geometry yet achieved, and will test the Kerr prediction at the percent level or better. In the infrared, the next generation of extremely large telescopes, including the 30-meter telescope and the extremely large telescope, will provide dramatically improved sensitivity for infrared observations of the galactic center. Combined with adaptive optics systems that correct for atmospheric blurring, these telescopes will detect fainter flares, measure more precise centroid tracks, and achieve better polarimetric sensitivity than current facilities. The increased faint flare detection rate will build larger statistical samples of flare events, allowing the quasi-periodic behavior to be characterized much more robustly than with current datasets. Improved infrared sensitivity will also enable better characterization of the stellar orbits in the nuclear star cluster, tightening the constraints on the black hole's mass and distance that underlie all other measurements. More precise mass and distance measurements will propagate into more precise predictions for the shadow size, the ISCO orbital period, and the lens-Thirring precession rate, allowing each of these observational tests to be conducted with better precision. The Gravity Plus upgrade to the Gravity instrument will extend its capabilities by improving the limiting magnitude for faint sources and by enabling observations of fainter flares that may occur at smaller radii closer to the black hole. This will probe the quasi-periodic behavior during fainter flares that may originate at smaller radii than the brightest events, potentially accessing the regime where quantum gravitational effects, if they exist at detectable levels, would be most prominent. In X-rays, the proposed Athena mission from the European Space Agency will provide a large collecting area combined with good energy resolution and temporal resolution. Athena will detect X-ray counterparts to fainter infrared flares than are currently accessible, building the multi-band picture of the flare physics in more detail. It will also enable better searches for echoes in the X-ray light curves, because X-ray flares can be short and bright enough that an echo at a time delay of minutes would be detectable above the background if the reflectivity is sufficiently high. In the gravitational waveband, LISA will complement the electromagnetic observations by probing the spacetime geodesics directly, independent of the plasma physics. If an extreme mass ratio inspiral occurs in the galactic center within LISA's mission lifetime, the combination of LISA gravitational wave data and EHT electromagnetic data for the same system would constitute an unprecedented multi-messenger test of the Kerr hypothesis and of the near-horizon physics. The investigation of the Sagittarius A anomaly has traced a path from the simple observation of a flickering pattern in infrared data through the systematic examination of instrumental and astrophysical explanations to the frontier where fundamental questions about gravity, information, and the nature of black holes become observationally accessible. The path has been organized by the discipline of exhausting conservative explanations before entertaining exotic ones, of demanding that each claim survive independent verification before being accepted, and of connecting every observational feature to a specific physical mechanism rather than allowing mysteries to accumulate without explanatory framework. What has emerged from this investigation is a hierarchy of understanding. At the top of the hierarchy is the established baseline of accreting black hole physics in strong gravity, which successfully accounts for the broad features of Sagittarius A*S observed behavior across all wavelengths. The ring size measured by the EHT, the stellar orbital periods measured by gravity, and the general character of the infrared and X-ray variability are all consistent with a 4 million solar mass black hole surrounded by a hot, radiatively inefficient accretion flow threaded by magnetic fields. At the next level are the anomalous features that the baseline model cannot fully explain. The quasi-periodic timing of centroid tracks and flare peaks, the smooth and large-amplitude polarization, angle rotations during flares, and the apparent coherence of the brightness distribution at preferred orientations in EHT images all point to a level of organization in the near-horizon accretion flow that standard turbulent accretion models do not naturally reproduce. These features are not definitively outside the range of what conventional physics can produce, but they are at the edge, requiring either rare conditions or underdeveloped aspects of the conventional models. At the next level are the physical mechanisms that could explain the anomalous features within the framework of conventional physics. The magnetically arrested disk scenario, kinetic reconnection physics, frame dragging and lens-thurring precession, and relativistic lensing of orbiting hotspots all contribute partial explanations. None provides a complete account of all the anomalous features simultaneously, but together they define the parameter space of conventional models that is compatible with the data and the directions in which those models need to be developed to fully account for the observations. At the frontier level are the genuinely new physical possibilities that the anomaly has made observationally relevant. Deviations from Kerr geometry, exotic compact objects without horizons, quantum near-horizon structure, and information-theoretic modifications of the near-horizon physics are all now quantitatively testable rather than purely speculative. The tests require better observations than currently available, but those observations are planned or under development, and the timeline for achieving them is a decade or less. The most honest summary of the current situation is that the anomaly is real in the sense that it persists across independent datasets and methods. It is at the right spatial and temporal scale to be physically significant, and it is not fully explained by the most carefully developed conventional models. But it is not yet definitively attributed to any specific physical cause, conventional or exotic. The investigation is ongoing, and its outcome will depend on measurements that have not yet been made. The scientific community studying Sagittarius A is in the position of having identified something genuinely interesting at the limit of current capabilities, and of having a clear path toward measurements that will either resolve the anomaly within conventional physics or establish it as a genuine departure from the expected behavior. The investments being made in next-generation telescopes, in improved simulation capabilities, and in better analysis methods are all motivated in part by the desire to resolve this specific question. The stakes are proportional to the possible answers. If the anomaly resolves into a specific plasma physics effect, such as kinetic reconnection in a magnetically arrested disk, then it will have driven the development of plasma physics in the extreme gravity regime to a new level of quantitative precision. That improvement will benefit not just Sagittarius A studies, but the entire field of black hole accretion physics and its application to active galactic nuclei, X-ray binaries, and the early universe. The understanding of how magnetically dominated plasma behaves near black holes is relevant to all of these systems. If the anomaly instead reveals a systematic deviation from the Kerr metric at the percent level, it will identify a specific signature of beyond general relativity physics in the strong field regime. That identification will guide theorists toward the specific class of alternative theories that is consistent with the observation, focusing a field that currently considers an enormous parameter space of alternatives without clear observational guidance. Finding the direction of the deviation is as valuable as finding the deviation itself, because it constrains the theoretical landscape rather than just revealing that the landscape is unexplored. If the anomaly reveals a reflecting or emitting surface near the gravitational radius, it will demonstrate that Sagittarius A is not a classical black hole in the mathematical sense, and it will launch a new era of investigation into what it actually is. The exotic compact object scenarios would move from theoretical curiosities to physically confirmed phenomena, and the implications for the information paradox, for quantum gravity, and for our understanding of the ultimate fate of gravitational collapse would be profound. The question of what lives inside the gravitational radius, which general relativity answers with a singularity in quantum gravity has not yet fully answered, would suddenly have observational inputs rather than being purely theoretical. The universe has revealed its secrets slowly, through patient observation and careful analysis, and it has rarely delivered the dramatic revelation that popular accounts prefer over the careful accumulation of evidence that science actually requires. The story of Sagittarius A is following that pattern. The anomaly is not a dramatic announcement. It is a persistent, subtle, carefully documented departure from the expected that demands explanation without yet providing one. It is exactly the kind of scientific situation from which genuine discoveries emerge, slowly and with difficulty, when the right measurements are made with the right precision. Every photon that reaches our telescopes from the galactic center carries in its frequency, its arrival time, and its polarization state a fragment of the story that the most extreme gravitational environment in our galaxy is trying to tell. The challenge is to listen carefully enough, with instruments sensitive enough and analyses rigorous enough, to hear the story clearly above the noise. Investigation is not finished. It is at the most productive and most uncertain stage, where the question is specific, the tools are almost adequate, and the answer is waiting in the data that the next generation of observations will collect. What began as a flickering pattern in the infrared light from the center of our galaxy has become the most precisely targeted observational attack on the fundamental nature of black holes and gravity that has ever been mounted. The flickering has not stopped. The timing is still wrong in ways that demand explanation, and the investigation continues, as science always continues, toward an answer that is not yet visible but is closer than it has ever been before. The center of the Milky Way is still flickering. And now, more than ever, we know exactly how to listen. The investigation has reached the stage where patience becomes the most demanding instrument in the entire toolkit. The anomaly is documented. The conservative explanations have been tested and found partially sufficient but not complete. The exotic possibilities have been identified and connected to specific observational tests. What remains is the hardest part of any scientific inquiry, the long work of accumulating evidence precise enough to settle the question definitively, while simultaneously developing the theoretical frameworks needed to interpret what the evidence reveals. This part of the investigation lives at the intersection of what we know and what we are capable of knowing, and the distance between those two things is where the most important science happens. The galactic center has been studied for decades, and the accumulation of knowledge about it has followed the pattern that characterizes mature scientific fields. Early work established the basic phenomenology, identifying Sagittarius A as a compact radio source, measuring the stellar orbits, and confirming the presence of a supermassive black hole. Subsequent work refined the measurements, improved the mass and distance estimates, characterized the variability, and built the theoretical framework for understanding hot, radiatively inefficient accretion. The most recent work has pushed into the regime where horizon-scale structure is resolved, and where the detailed predictions of general relativity can be tested against direct observations of the near-horizon environment. Each phase of this progression has raised new questions while answering old ones. The discovery of the stellar orbits raised the question of what the central mass was made of. The confirmation of the black hole interpretation raised the question of how accretion operates in the low-luminosity regime. The characterization of the variability raised the question of whether the quasi-periodic behavior was real and physically meaningful. The resolution of the shadow raised the question of whether the spacetime is exactly Kerr. And the identification of the anomaly has raised the question of whether the horizon itself is what we have always assumed. This sequential deepening of questions is not a sign of failure. It is the signature of a healthy scientific program that continually reaches new depths by building on what has been established. Each answered question creates the foundation for the next question, and the questions become more fundamental as the observations become more precise. The investigation of Sagittarius A has reached the level where the next questions touch the deepest principles of physics, which means that the observational program is working exactly as it should. The challenge of this phase is that the most fundamental questions are also the most difficult to answer observationally. Testing the care metric at the percent level requires instruments that do not yet exist. Detecting or ruling out echoes at the few percent amplitude level requires sensitivity and temporal resolution that are at the edge of what future facilities will achieve. Connecting the electromagnetic observations to gravitational wave measurements requires waiting for events that may or may not occur during the relevant observational windows. The science is demanding not just technical excellence, but a kind of patient commitment to a long-term program that extends beyond the career of any individual scientist. This is one of the places where the social structure of science becomes as important as its intellectual content. The observational programs needed to resolve the Sagittarius A anomaly require the sustained collaboration of large international teams over timescales of a decade or more. They require the construction of expensive new facilities whose scientific justification depends partly on questions that are not yet fully formulated because the questions emerge from the data that will be collected. They require the training of new generations of scientists who will carry the investigation forward when the current generation of researchers has moved on to other problems. The Event Horizon Telescope collaboration is an example of how this kind of sustained, large-scale scientific effort can succeed. It grew from a small community of radio astronomers into a global collaboration of hundreds of scientists from dozens of institutions across multiple countries, unified by the shared goal of imaging the shadow of a supermassive black hole. The effort took more than a decade from conception to the first published images, and the collaboration has continued to grow and improve its capabilities since the first results were published. The pattern of sustained investment and gradual capability improvement is the model that the Sagittarius A anomaly investigation will need to follow. The theoretical side of the investigation faces its own version of this challenge. The theoretical tools needed to fully understand the near-horizon environment of Sagittarius A span an enormous range of scales and physical regimes, from the large-scale dynamics of the accretion flow captured by global MHD simulations, to the kinetic physics of electron acceleration captured by particle-in-cell simulations, to the quantum gravitational effects that may or may not modify the near-horizon structure. No single theoretical framework currently spans this entire range, and developing one will require sustained investment in both theoretical physics and computational infrastructure. The most urgent theoretical need is for a better understanding of how kinetic physics couples to the global accretion dynamics in the hot, tenuous plasma near Sagittarius A. Current global simulations treat the electron distribution function using prescribed recipes that capture the gross features of the emission, but miss the detailed physics of particle acceleration and the resulting non-thermal tails. Improving these recipes requires input from kinetic simulations that model the relevant processes from first principles, and translating that input into global simulation prescriptions requires a theoretical framework for how kinetic effects average out at the fluid level. This is a technically demanding problem that sits at the intersection of plasma physics, numerical relativity, and radiation transport, and it has attracted the attention of a growing community of researchers who recognize it as central to the interpretation of current and future observations. The development of better kinetic physics prescriptions for global simulations is not just relevant to the Sagittarius A** anomaly. It is relevant to a broad range of astrophysical systems, including other low-luminosity active galactic nuclei, relativistic jets, and the hot intracluster medium in galaxy clusters. The investment in better kinetic physics pays dividends across astrophysics rather than just for one source, which provides additional motivation for the effort and broadens the community of researchers who are working on it. The question of what makes the Sagittarius A anomaly specifically interesting, as opposed to variability in other accreting sources, comes back to a feature that has been mentioned but deserves deeper examination. Sagittarius A is unusual among accreting black holes in that its characteristic variability timescales are accessible to human observers without any technology beyond a sensitive telescope and a patient-watching strategy. The orbital period at the innermost stable circular orbit, the relevant timescale for the anomaly, is tens of minutes. That is the length of a coffee break, a short meeting, a chapter in an audiobook. This immediacy is not just aesthetically convenient. It has a deep physical significance. The timescale of the anomaly is set by the gravitational radius of the black hole divided by the speed of light, scaled by the numerical factor that determines the ISCO location. For Sagittarius A asterisk, that combination produces a timescale of tens of minutes. For a stellar mass black hole, the equivalent timescale would be milliseconds. For the supermassive black hole in M87, it would be days. Sagittarius A occupies a unique intermediate position where the characteristic timescale is human accessible and where the source is close enough for the horizon scale to be resolved with Earth-sized interferometry. This combination of accessible timescale and resolvable horizon scale exists nowhere else in the accessible universe. Other nearby supermassive black holes in the local universe are either much less massive, making them too dim and too fast to study easily, or much more massive, making the horizon scale too small on the sky despite the larger physical size. Sagittarius A sits in a sweet spot that the universe has provided, and this sweet spot is what makes the anomaly scientifically tractable rather than permanently inaccessible. The accessibility of the timescale also means that the observational dataset can grow rapidly. In a system where the relevant timescale is milliseconds, building a large statistical sample of events requires only a few minutes of observation. In a system where the timescale is days, building an equivalent sample requires years. For Sagittarius A with a timescale of tens of minutes, a single night of continuous observing can capture several complete cycles of the anomalous pattern, and a season of observations can build a sample of dozens of independent events. This growth rate is fast enough that the statistical significance of the anomaly can be definitively assessed within a few years of intensive monitoring. The temporal accessibility also enables a specific kind of analysis that would be impossible for systems with longer timescales. Real-time event detection and immediate follow-up observing can be employed for Sagittarius A in a way that mimics the rapid response programs used for gamma-ray bursts and gravitational wave transients. When the infrared monitoring system detects the beginning of an unusual flare, it can trigger simultaneous observations with other facilities before the flare has reached its peak. This enables coordinated multiband measurements of individual flares from the rising phase through the peak and into the decay, building a complete picture of each event rather than catching only part of it. Triggered observing programs have already been employed for Sagittarius A with partial success, limited mainly by the reaction time required to communicate between facilities and reconfigure instruments. Future programs will reduce this reaction time by using automated triggering systems that can alert multiple facilities simultaneously when predefined criteria are met. The criteria can include the brightness threshold, the rate of rise, and the polarization behavior during the rising phase, allowing the triggering to be tuned to catch the specific kind of events that are most diagnostic for the anomaly. Automated triggering also removes the selection bias that affects manually triggered observations. When a human decides to call for follow-up observations, that decision is influenced by a complex mixture of scientific judgment, availability, and the psychological tendency to act when the signal appears strong. An automated system applies the same criteria to every event regardless of the observer's state, the time of day, or the perceived excitement level. This consistency is important for building a clean statistical sample, because a sample collected by inconsistent human decisions can be biased in subtle ways that are difficult to correct after the fact. The construction of a clean, unbiased statistical sample of well-characterized flare events is the most important near-term scientific goal for the electromagnetic investigation of the Sagittarius A asterisk anomaly. The existing literature contains many individual well-documented events, but the collection has been assembled opportunistically rather than systematically. Some flares were caught because instruments happened to be pointing at the galactic center for unrelated science goals. Others were targeted because previous events had suggested that a particular night was promising. The resulting sample is not representative of the full population of flare events, and the anomaly's statistical significance cannot be fully assessed without a representative sample. A systematic monitoring program would address this by observing the galactic center on a predefined schedule, independent of predictions about whether interesting events will occur. The cadence and sensitivity of the monitoring determine what fraction of the flare population is captured and what the minimum detectable amplitude is. With sufficient monitoring, the distribution of flare amplitudes, durations, quasi-periods, and polarization properties can be characterized as a whole population rather than as a cherry-picked subset of particularly interesting events. The anomaly's recurrence rate within this population is the most meaningful measure of its statistical significance. Such a program requires dedicated telescope time at infrared facilities, which are in high demand for a wide range of scientific programs. Securing the necessary time requires making a compelling case to telescope allocation committees that the scientific return justifies the investment, and that case becomes stronger as the evidence for the anomaly accumulates. The scientific community has been building that case over the past several years, and the growing recognition of the anomaly as a significant result has made the argument for dedicated monitoring time more persuasive. The theoretical landscape of what the anomaly might reveal has a structure that is worth exploring more carefully, because the different possible explanations have different implications not just for Sagittarius A, but for our understanding of black holes throughout the universe. The implications scale from the local and practical to the cosmological and fundamental, and understanding the full range helps clarify why the investigation matters beyond its immediate observational context. At the most local and practical level, understanding the near-horizon accretion physics of Sagittarius A improves our ability to model other low-luminosity, active galactic nuclei. These systems, which include most nearby galaxy centers including our own, are important for understanding the coevolution of black holes and their host galaxies. The feedback between accreting black holes and the surrounding galaxy, through jets, winds, and radiation, regulates star formation rates and shapes the properties of the galaxy over cosmic time. Getting the physics of this feedback right requires understanding how black holes accrete in the low-luminosity regime, and Sagittarius A is the only source close enough for the detailed study needed to validate or improve the relevant models. The models developed from studying Sagittarius A are applied to interpret observations of thousands of other low-luminosity active galactic nuclei across cosmic distances. If those models are wrong in ways revealed by the Sagittarius A anomaly, then all the inferences drawn from applying them to more distant sources need to be revisited. The impact is not confined to understanding one black hole. It propagates through the entire field of galaxy evolution and black hole demography. At an intermediate level, understanding the nature of the Sagittarius A anomaly constrains the range of objects that can masquerade as black holes in galactic centers throughout the universe. If the nearest example of a supermassive black hole turns out to be an exotic compact object rather than a true black hole, then the fraction of apparent black holes in galaxy centers that might similarly be exotic objects becomes a live question. Accounting for the possibility of exotic compact objects could change the inferred black hole mass function and the history of black hole growth through cosmic time. This is not a purely academic concern. The supermassive black hole mass function, derived from observations of galaxy centers across cosmic time, is used to constrain models of black hole formation and growth, to estimate the contribution of black hole accretion to the cosmic X-ray background, and to predict the rate of gravitational wave events that will be detectable by LISA. If a significant fraction of the objects counted as black holes are actually exotic compact objects with different accretion physics and different gravitational wave signatures, these predictions would need substantial revision. At the cosmological level, the question of whether horizons are truly the final state of gravitational collapse connects to the history of entropy and the arrow of time in the universe. Black holes are entropy-producing objects that transform complex, structured matter into simple thermal states. If information is genuinely destroyed at the horizon, this represents an irreversible increase in entropy that is not balanced by any corresponding decrease elsewhere. The second law of thermodynamics says that total entropy cannot decrease, so information destruction at horizons would be consistent with the second law. But it would also mean that the universe's evolution is genuinely irreversible in a fundamental sense, that the past cannot, even in principle, be reconstructed from the present. If instead information is preserved, either by being encoded in subtle correlations in the Hawking radiation, or by being stored in a modified near-horizon structure, or by not being absorbed at all in the case of exotic compact objects, then black holes are not true entropy producers in the fundamental sense. They would be entropy transformers that convert structured information into a form that is practically inaccessible but theoretically recoverable. The difference between destruction and inaccessibility has profound implications for the nature of time, causality, and physical law. These cosmological implications may seem disconnected from the specific observations of Sagittarius A, but they are not. Every measurement that constrains the nature of the near-horizon environment of a real black hole provides an input to the theoretical debate about information and entropy. Detection of echoes from Sagittarius A would demonstrate that information is not being absorbed at the horizon, directly addressing the paradox. A measurement of a modified shadow that deviates from the Kerr prediction would constrain the class of alternative spacetimes available to resolve the paradox. Even a null result, ruling out echoes and confirming the Kerr metric, would not resolve the paradox theoretically, but would constrain its resolution to mechanisms that do not produce observable deviations at current precision. The connection between the Sagittarius A anomaly and the information paradox is therefore not metaphorical but literal. The same observational evidence that constrains the near-horizon accretion physics constrains the viability of specific proposals for resolving the paradox. And the proposals that survive the observational constraints are the ones that theoretical physicists should focus on developing, because they are the ones that the universe has not yet ruled out. The precision required to resolve the anomaly definitively demands understanding and controlling systematic errors at levels that push the current limits of instrumentation and data analysis. Systematic errors are those that bias measurements in a consistent direction rather than randomly in both directions, and they are more dangerous than random errors because they cannot be reduced simply by collecting more data. A systematic error that is 10 times smaller than the current measurement uncertainty is harmless today, but becomes the dominant limitation when the random errors are reduced by a factor of 10 through better instrumentation. Identifying and controlling systematic errors requires understanding every step of the measurement process at a level of detail that goes beyond what is needed for simply collecting and analyzing data. For the EHT, systematic errors arise from many sources. Station-based errors, including phase drifts, gain variations, and polarization leakage, must be characterized using calibrator sources observed near in time and sky position to Sagittarius A. Atmospheric errors, including tropospheric water vapor and ionospheric electron density fluctuations, introduce additional phase noise that must be tracked using GPS measurements, water vapor radiometers, and simultaneous monitoring of point-like calibrator sources. Source structure errors, where the reconstruction algorithm invents features that are not in the source, must be identified using synthetic data tests where known source models are processed through the same pipeline. For gravity, systematic errors arise from the precision of the baseline measurement between the 4 VLT telescopes, from the accuracy of the phase reference transfer from the bright reference star to the faint flare, and from the accuracy of the wavelength calibration that converts phase differences into position differences. The baseline measurement requires knowing the separation between telescopes to a precision of a fraction of a wavelength, which is a fraction of a micrometer at infrared wavelengths over baselines of hundreds of meters. Achieving this precision requires continuous monitoring of baseline variations caused by thermal expansion and contraction of the telescope structure as temperatures change during the night. The phase reference transfer is particularly critical for faint flare astrometry because Sagittarius A is too faint during quiescence to serve as its own phase reference. Instead, a bright nearby star is used as the reference, and the phase of Sagittarius A *S emission is measured relative to that reference. Any error in characterizing the reference star's position propagates directly into the inferred position of Sagittarius A, creating a systematic offset that cannot be distinguished from a real source position shift by the astrometry alone. The reference star's position must be known to microarcsecond precision from independent measurements, which requires its own chain of calibration extending from global reference frames established by radio interferometry of extragalactic sources. For X-ray timing, systematic errors arise from the accuracy of the satellite's onboard clock, from the modeling of photon arrival time corrections due to the satellite's orbit around Earth, and from the accuracy of the background subtraction in the vicinity of the bright galactic center region. The onboard clock is typically accurate to microseconds, which is more than adequate for detecting the minute-scale quasi-period of the anomaly, but systematic drifts in the clock's rate can introduce apparent periodicities if not properly corrected. Background subtraction is particularly challenging near the galactic center, which is crowded with unrelated X-ray sources that contribute to the background in the region around Sagittarius A. The comparison between datasets from different instruments and different epochs requires a common reference frame that ties all measurements together consistently. For astrometry, this means adopting a common coordinate system based on the positions of reference objects measured with respect to an extragalactic frame that has no proper motion. For timing, this means adopting a common time standard that accounts for the Earth's motion around the Sun and the satellite's orbit around Earth. For spectroscopy, this means adopting a common wavelength calibration based on known atomic transitions measured in laboratory experiments. The consistency of these reference frames across different datasets is a potential source of systematic error that must be verified by cross-checking overlapping measurements. The process of verifying systematic error control is itself a scientific contribution because it develops methods and standards that benefit the entire field beyond the specific problem being studied. The techniques for phase referencing, baseline metrology, and image reconstruction developed for the EHT and gravity programs have applications to a wide range of interferometric observations. The calibration standards developed for precise timing analysis apply to all time-domain astronomy. The background subtraction methods developed for crowded field X-ray analysis apply to galactic center studies across many wavelengths. This spillover of methodological development from one specific program to the broader field is one of the less celebrated but very real benefits of investing in difficult frontier observations. The methods required to push to the next level of precision always turn out to be useful for multiple problems, and the community that develops them gains a capability advantage that extends well beyond the original motivation. The sociology of the scientific community working on the Sagittarius A anomaly reflects the complexity and importance of the question being studied. The community spans multiple disciplines including radio astronomy, infrared astronomy, X-ray astronomy, plasma physics, numerical relativity, particle physics, and theoretical high-energy physics. These disciplines have different cultures, different standards for evidence, different publication norms, and different expectations about what constitutes a significant result. Managing the communication and collaboration across these disciplinary boundaries is a non-trivial challenge that affects the pace and quality of scientific progress. Observational astronomers are trained to demand statistical significance at levels of multiple sigma and to scrutinize every claim of a new detection for potential artifacts. Theoretical physicists are more comfortable with speculative hypotheses and are trained to develop frameworks that might apply before the evidence is definitive. Plasma physicists focus on the detailed microphysics of the near-horizon environment and are often skeptical of inferences that require assumptions about plasma behavior to be simpler than they actually are. Numerical relativists worry about whether the equations being solved accurately represent the physical situation and whether the numerical resolution is adequate. Each perspective is valuable, and none is sufficient alone. The history of the field includes instances where the different disciplinary perspectives led to significant disagreements about the interpretation of evidence. The initial discovery of quasi-periodic behavior in some X-ray binaries was disputed between theorists who saw it as evidence for specific orbital resonances and observers who saw it as statistical fluctuations in red noise processes. The debate took years to resolve and required both better data and better statistical methods. A similar dynamic is playing out for the Sagittarius A anomaly, with different community members holding different priors about how seriously to take the evidence and different views about which theoretical framework is most appropriate. These disagreements are not pathological. They are the normal process by which scientific communities sort through complex evidence and converge on the most defensible interpretation. The key is that the disagreements are conducted through the scientific method, through the specification of clear hypotheses, quantitative predictions, and observations that can distinguish between them. When the disagreements are driven by differences in prior probability assignments or by differences in standards for statistical significance, they can often be resolved by agreeing in advance on a specific test and then conducting it. This kind of pre-commitment to a decision procedure is difficult to implement in practice because scientists have strong priors that are hard to set aside, but it is the ideal toward which collaborative investigation should aim. The Sagittarius A community has taken steps in this direction by organizing specific working groups within the EHT collaboration and the gravity collaboration to evaluate the evidence for and against the anomaly using agreed-upon methods. These groups include members with different prior views and use analysis pipelines that have been reviewed and validated before being applied to the data. The results of these working groups have more credibility than individual analyses precisely because they have been conducted with methodological consensus, even when the conclusions remain disputed. The peer review process plays an important role in this context by providing an external check on claims before they are published. Peer reviewers can identify methodological problems, question interpretations, demand better statistical analysis, and request additional tests that the authors might not have considered. This external check is imperfect because reviewers are human and can have their own priors and biases, but it provides a layer of quality control that filters the most obvious problems before they enter the scientific record. For a claim as significant as the Sagittarius A anomaly, multiple rounds of peer review and multiple independent analyses are expected before the community converges on a consensus interpretation. The public communication of the investigation requires special care because the topic sits at the intersection of established science and speculative physics in a way that can easily be misrepresented. A measurement that provides modest evidence for a quasi-periodic signal can be accurately described as suggesting a pattern that deserves further investigation, or it can be inaccurately described as proving that black holes behave differently than expected or that general relativity is wrong. The difference between these descriptions is the difference between honest scientific communication and sensationalism, and the scientific community has an obligation to maintain that distinction even when the honest description is less exciting. At the same time, the scientific community has an obligation to communicate the genuine excitement and importance of the investigation to the public, because the public funds the telescopes and the research programs that make the investigation possible. The balance between accuracy and engagement is not always easy to strike, but it is necessary for maintaining public trust in science and for sustaining the long-term investment that programs like the EHT and gravity require. The Sagittarius A investigation is itself a compelling story, one of humanity's most ambitious attempts to understand the most extreme environments in the universe, and that story can be told honestly and engagingly without exaggerating the conclusions. Looking forward, the trajectory of the investigation over the next decade points toward a resolution, not in the sense of a dramatic single discovery, but in the sense of a convergence of evidence that will make one interpretation substantially more likely than the others. The convergence will come from multiple directions simultaneously, each constraining the hypothesis space from a different angle, until the remaining viable interpretations are few and specific enough to be definitively tested. The photon ring measurement will constrain the near-horizon metric deviation from Kerr at the percent level, ruling out or confirming specific classes of alternative spacetimes. The echo search will push the reflectivity of any potential surface below the percent level, constraining the parameter space of exotic compact objects. The extreme mass ratio inspiral detection by LISA, if it occurs, will provide geodesic precision tests of the Kerr hypothesis that go beyond what electromagnetic observations can achieve. The improved GRMHD simulations, incorporating better kinetic physics, will either reproduce the anomaly within conventional plasma physics or identify the specific feature of the accretion physics that would need to be modified. Each of these lines of evidence is independently informative, but their combination will be decisive in a way that none can achieve alone. If all lines of evidence converge on the Kerr hypothesis with conventional plasma physics, the anomaly will be understood as a consequence of sophisticated plasma dynamics in a magnetically organized accretion flow, and the investigation will have driven the field of strong gravity plasma physics to a new level of quantitative precision. If some lines of evidence consistently point away from the Kerr hypothesis, while others are consistent with it, the pattern of deviation will identify which specific aspect of the near-horizon physics is non-standard and will guide the development of more complete theoretical frameworks. The possibility that the investigation reveals something genuinely unprecedented, something that does not fit any of the current theoretical frameworks, cannot be excluded. Science has repeatedly encountered situations where observations outran theory, where the data demanded explanations that required conceptual innovations rather than incremental refinements of existing frameworks. The history of black hole physics is itself full of such moments, from the initial disbelief that singularities were physical to the discovery of Hawking radiation to the information paradox. The Sagittarius A anomaly may be the next such moment, or it may resolve cleanly within existing frameworks. Either outcome would be valuable, and either outcome is possible. What is not possible, given the current state of evidence, is to close the investigation without continuing it. The anomaly is too persistent and too significant to be dismissed without definitive resolution, and the tools to achieve that resolution are being built. The investigation will continue, as it must, until the question is answered or until it is replaced by a deeper question that makes the current one appear, in retrospect, as a necessary step toward a more complete understanding. The galactic center will continue to flicker. Sagittarius A will continue to flare and fade, to rotate its polarization and trace its centroid paths against the crowded stellar background. Each photon that reaches our telescopes from that direction carries a fragment of an answer that we are gradually learning to read. The reading is slow and careful and demands the best instruments and the best methods and the best minds that the scientific enterprise can bring to bear, but it is progressing, and the direction it is pointing is toward the most fundamental questions about the nature of black holes, gravity, information, and the structure of physical reality. That direction is worth following wherever it leads. Not because the destination is guaranteed to be revolutionary, but because the journey itself is expanding the range of questions that can be asked with quantitative precision about the universe's most extreme environments. An expansion of the range of precisely askable questions is, ultimately, what scientific progress means. The center of the Milky Way has been flickering for billions of years, long before any eye existed to notice it. For a few decades, human civilization has had the instruments to detect that flickering and the intelligence to ask what it means. We are using both. The flickering continues, and so does the asking, and the space between them is where understanding grows. The anomaly is not a mystery that will remain mysterious forever. It is a question that is being answered, carefully and rigorously, by a community of scientists who have committed the extraordinary technical and intellectual resources needed to follow the signal to its source. When the answer comes, it will be the result of decades of work by thousands of people using instruments that represent the highest achievements of human engineering and the most sensitive measurements ever made of the most extreme natural environment accessible to observation. That answer, whatever it turns out to be, will change what we know about the universe. And the flickering at the center of our galaxy will be its herald, the first signal that something important was waiting to be understood at the edge of the deepest darkness we have ever learned to see. The story of the Sagittarius A anomaly is, at its core, the story of what happens when human curiosity meets the limits of human knowledge and refuses to stop there. It is the story of instruments built to impossible specifications, of algorithms designed to extract images from interference patterns, of teams assembled across continents and disciplines to address a question that no single person or institution could answer alone. It is the story of patience applied to a source that flickered for billions of years before we were able to notice, and of rigor applied to signals so faint that distinguishing them from noise requires the most careful analysis yet attempted in the history of astronomy. The anomaly itself is a pattern, a preference for certain timescales and orientations and polarization, behaviors that persists across independent datasets and resists the many explanations that have been constructed to account for it. It is not a dramatic signal that announces itself loudly and demands immediate attention. It is a subtle, recurring suggestion that something near the event horizon of Sagittarius A is more organized than it should be, more structured than turbulence alone can explain, more coherent than the simplest models of magnetized plasma allow. Following that suggestion has led the investigation through the entire landscape of black hole physics, from the established baseline of general relativistic accretion to the frontier, where quantum gravity and the information paradox meet observational astronomy. Along the way, the investigation has identified specific gaps in the current theoretical understanding, motivated specific improvements to the numerical simulation methods, defined specific observational tests for the next generation of instruments, and connected the near-horizon physics of one black hole to the deepest questions about the nature of gravity and information. This is what good anomalies do. They do not just identify a discrepancy. They illuminate the structure of the problem by showing exactly where the current understanding falls short and exactly what kind of new understanding would be needed to resolve the discrepancy. The Sagittarius A anomaly has done this with unusual clarity, pointing simultaneously toward improvements in plasma physics, in spacetime metric testing, in the search for non-classical compact objects, and in the connection between electromagnetic and gravitational wave astronomy. The investigation is not finished. The anomaly is not explained. The flickering at the center of the Milky Way continues, and the question it poses remains open. But the question is now posed more precisely than ever before. The tools to answer it are better than they have ever been, and the community pursuing the answer is larger and more capable than at any previous point in the history of galactic center research. Every measurement of Sagittarius A brings the answer closer. Every improvement in instrument sensitivity, every new analysis method, every improved simulation adds to the pressure on the anomaly to reveal its origin. The pressure is building, the tools are improving, and the answer is somewhere in the flickering that has always been there, waiting to be read by those patient and capable enough to read it. The center of our galaxy is speaking. We are learning to listen. The investigation has now traveled from the first anomalous flicker in the infrared data through the systematic examination of plasma physics, spacetime geometry, exotic compact objects, and quantum gravity. It has identified the specific observational tests that will resolve the question, and it has described the instruments being built to conduct those tests. What remains is to synthesize everything the investigation has uncovered into a coherent account of where the science stands, what the anomaly has taught us regardless of its ultimate explanation, and what the resolution of this specific question means for the broader project of understanding the universe. Synthesis is not summary. Summary lists what was said. Synthesis identifies what the saying means and why it matters beyond the immediate context. The Sagittarius A anomaly has accumulated enough evidence, enough theoretical development, and enough methodological refinement that synthesis is now possible in a way that was not possible at the beginning of the investigation. The pieces are assembled. The question is what picture they form. The first element of the synthesis is the recognition that the anomaly has already changed the field regardless of how it is ultimately explained. Before the anomaly was identified and documented, the near-horizon environment of Sagittarius A was treated in most theoretical and observational work as a place where standard hot accretion physics applies in a straightforward way. The magnetic field was assumed to be turbulent, the electron distribution was assumed to be approximately thermal, the variability was assumed to be stochastic without preferred timescales, and the horizon was assumed to be a featureless absorbing boundary. These assumptions were not unreasonable given the available evidence, but they were assumptions rather than established facts, and they led to theoretical models that were simpler than the real system turns out to be. The anomaly has forced a revision of each of these assumptions. The magnetic field near Sagittarius A appears to be more organized than a purely turbulent model would predict, with persistent preferred orientations that show up in both the millimeter polarization and the infrared polarization during flares. The electron distribution appears to include a significant non-thermal component that is produced intermittently by magnetic reconnection, and that dominates the bright flare emission, even though it represents a small fraction of the total electron population. The variability shows a quasi-periodic structure at the timescale of the innermost stable circular orbit that is too coherent to be fully explained by red noise turbulence. And the horizon, if it exists as the classical model predicts, has been tested at a level of precision that has constrained but not yet ruled out the possibility that it is replaced by a surface with reflecting or emitting properties. Each of these revisions is scientifically valuable independent of whether the anomaly ultimately points toward plasma physics or toward new gravitational physics. A more realistic model of the magnetic field organization near accreting black holes improves our understanding of jet formation, because jets are thought to be powered by organized magnetic fields threading the horizon. A better characterization of non-thermal electron populations improves our ability to interpret the spectra of other accreting systems where the same physics operates, but where the detailed constraints available for Sagittarius A are not accessible. A statistical characterization of the quasi-periodic variability and its relationship to the magnetic flux state of the accretion flow provides constraints on the theoretical models of magnetically arrested disks that apply broadly to other low-luminosity active galactic nuclei. The methodological advances driven by the anomaly investigation are also broadly valuable. The development of improved reconstruction algorithms for EHT data that can handle source variability during the observation benefits any future EHT target that shows rapid evolution. The development of triggered multiband observing strategies that can respond automatically to flare events in the infrared benefits the entire field of time-domain astronomy. The development of better statistical methods for detecting quasi-periodic signals in red noise processes applies to QPO searches in X-ray binaries, millisecond pulsars, and other variable sources. The development of precise echo search methods applies to gravitational wave echo searches and to echo searches in other accreting systems. These methodological spillovers mean that the investment in studying the Sagittarius A anomaly has already generated returns that extend well beyond the specific question being addressed. This is the normal pattern of frontier science, where the methods developed to address one hard problem turn out to be useful for many other problems. But it is worth making explicit because the return on investment in science is not always visible in the direct product of the research. The indirect returns from methodological innovation often exceed the direct returns from the specific discovery, and the Sagittarius A anomaly investigation is a clear example of this pattern. The second element of the synthesis concerns what the anomaly has revealed about the relationship between theory and observation in modern astrophysics. The investigation began with observations that did not fit the simplest theoretical models and proceeded by developing more sophisticated models that could account for more of the observations. At each stage, the models made predictions that could be tested by new observations, and the new observations either confirmed those predictions or demanded further model refinement. This iterative dialogue between theory and observation is the essence of the scientific method, but it operates differently in astrophysics than in laboratory science because the experimenter cannot control the source. In a laboratory experiment, the experimenter can vary one parameter at a time, holding all others constant, to isolate the effect of that parameter. This controlled variation is the foundation of the experimental method as traditionally conceived, and it allows causal relationships to be established with confidence. In astrophysics, the source is not under the experimenter's control. The experimenter can only choose when and how to observe, not what the source does. The galactic center does not cooperate with controlled experiments. It varies when it wants, in the bands it chooses, at the amplitude it generates, and the observer must be patient and sophisticated enough to extract the relevant physics from the uncontrolled variation. This limitation is partly compensated by the variety of physical conditions that astrophysical sources naturally provide. Sagittarius A explores a wide range of accretion states, magnetic field configurations, and electron distributions without any intervention from the observer. By observing the full variety of states and correlating the properties of different states with each other, it is possible to build a multidimensional picture of the system that is analogous in some ways to the multivariable mapping that controlled experiments achieve in a laboratory. The difference is that the mapping in astrophysics is statistical, requiring many observations to establish the correlations, rather than being established by a single controlled experiment. Quasi-periodic anomaly is a particularly clear example of this statistical mapping approach. By accumulating many flare observations and examining the distribution of quasi-periods, amplitudes, polarization angles, and centroid track shapes, the investigation is building a statistical characterization of the inner accretion flow that is constrained by all the observations simultaneously. Individual observations are ambiguous. The population of observations is much more constraining. This is why the systematic monitoring program described earlier is so important. It is the astrophysical analog of the controlled experiment, not controlling the source, but controlling the sampling so that the resulting dataset is unbiased and representative. The theoretical side of this dialogue has also been transformed by the anomaly. Before the anomaly was identified, the theoretical literature on hot accretion flows was dominated by models that were calibrated to reproduce the broad spectral energy distribution and the overall variability statistics. These models were not wrong, but they were not required to reproduce the detailed timing and polarization behavior of individual flares, because that behavior had not been characterized precisely enough to serve as a constraint. The anomaly changed this by providing specific, quantitative constraints on the model predictions that go beyond the broad spectral shape. A model that correctly predicts the spectral energy distribution, but incorrectly predicts the quasi-periodic timescale, is now understood to be incomplete, even if it was previously considered adequate. A model that correctly predicts the overall variability statistics, but incorrectly predicts the polarization behavior during flares, is similarly incomplete. The anomaly has raised the bar for what counts as a successful model, and that higher bar has driven the theoretical community to develop more physically complete descriptions of the near-horizon accretion flow. This raising of the theoretical bar is precisely what observational anomalies are supposed to do. A measurement that is consistent with all existing models provides no information about which model is correct and no motivation to improve the models. A measurement that is inconsistent with the simplest models, but consistent with more sophisticated ones, identifies which physical processes need to be included and at what level of detail. And a measurement that is inconsistent with all existing models demands theoretical innovation. The Sagittarius A anomaly has been playing this role, pushing the theoretical community from simple turbulent accretion models to sophisticated magnetically organized accretion models, and from simple Kerr geometry assumptions to careful metric deviation testing. The third element of the synthesis addresses the relationship between the Sagittarius A investigation and the broader question of what black holes are. This question might seem to have been answered definitively by the stellar orbit measurements, the EHT imaging, and the decades of supporting evidence that collectively establish Sagittarius A as a supermassive black hole, and in one important sense, the question has been answered. There is a concentration of 4 million solar masses at the galactic center, confined to a region smaller than the solar system, that dominates the gravitational dynamics of the nuclear star cluster and casts a shadow consistent with the photon orbit of a classical black hole. These facts are established beyond reasonable scientific doubt. But the question of what black holes are has a deeper layer that the established facts do not yet fully address. The question is not just whether a black hole is present, but whether the specific mathematical structure of a classical black hole, the exact Kerr metric with its smooth event horizon, its absence of any surface, and its perfect one-way information absorption, accurately describes the physical reality at the center of the Milky Way. This deeper question is not answered by the current evidence, and it is precisely the question that the anomaly investigation is targeting. The distinction between these two levels of the question is important because they have different evidential thresholds and different implications. Establishing that a 4 million solar mass compact object exists at the galactic center required decades of patient stellar orbit monitoring and can be done with infrared telescopes. Establishing that this compact object is exactly described by the Kerr metric requires horizon-scale precision measurements that test the spacetime geometry at scales that have only recently become accessible. The two questions are not the same, and conflating them would lead to the mistaken belief that the question is already answered when it is only partially answered. The partial answer that we have is enormously valuable. It tells us that general relativity works well enough at the galactic center to predict the shadow size and the stellar orbit shapes. It tells us that the compact object has properties consistent with those of a Kerr black hole when measured at the precision currently available. It tells us that the most obvious deviations from the Kerr metric, those large enough to significantly change the photon orbit radius or the stellar orbit shapes, are not present. This partial answer rules out a large class of exotic alternatives and focuses the investigation on alternatives that mimic the Kerr metric closely enough that the differences require precision measurements to detect. The anomaly provides the first specific observational indication that the partial answer may not be the complete answer. If the quasi-periodic signal in the near-horizon emission reflects a physical mechanism that cannot be fully explained by conventional plasma physics in the Kerr spacetime, then the complete answer to what Sagittarius A is may be different from the partial answer that the current evidence supports. But this is a conditional statement that depends on whether the anomaly survives the systematic investigation of conventional plasma physics explanations. Until that investigation is complete, the conditional cannot be converted into a definitive claim. What the investigation has done is to make the conditional a scientifically precise and testable one. The question is no longer a vague philosophical uncertainty about whether black holes are really what we think they are. It is a specific observational question about whether the quasi-periodic signal in the Sagittarius A emission can be explained by conventional plasma physics in the Kerr spacetime, or whether it requires modifications to the spacetime, to the plasma physics, or to both. That specificity is what makes the question scientifically productive rather than merely philosophically interesting. The fourth element of the synthesis looks at the timescale and the difficulty of the investigation from a broader perspective. The history of science includes many examples of fundamental questions that took decades or centuries to resolve from the time they were first posed to the time the answer was established with sufficient precision to be widely accepted. The question of whether the Earth moves was posed by Copernicus in a form that could be answered observationally, but the final observational confirmation through stellar aberration and stellar parallax came almost 3 centuries later. The question of whether gravity bends light was predicted by general relativity in 1915 and confirmed observationally in 1919, a timescale of 4 years that was rapid by historical standards. The question of whether gravitational waves exist was predicted by Einstein in 1916 and directly detected a century later in 2016. The question of whether black holes exist in the mathematical sense predicted by general relativity, with true event horizons that absorb information irreversibly, is a question that has been building toward an answer for decades. The observational tools needed to address it at the precision required have only recently become available, and the theoretical frameworks needed to interpret the observations are still being developed. Based on the historical pattern, it would not be surprising if the definitive resolution of this question takes another decade or two, even with the significant advances in instrumentation and methods that are underway. This timescale expectation is not pessimism. It is a realistic assessment based on the difficulty of the measurement and the complexity of the interpretation. The question is hard because it sits at the intersection of multiple complex physical processes that are individually difficult to model and collectively even harder to disentangle. The measurement is hard because it requires reaching spatial and temporal resolutions that push the limits of what current and near-future instrumentation can achieve. The interpretation is hard because the signal of interest, a subtle modification of the near-horizon emission pattern, must be extracted from a much louder background of conventional plasma variability. Given this realistic assessment, the most important thing the scientific community can do is maintain the momentum of the investigation through the difficult middle period when evidence is accumulating, but the answer is not yet clear. This means continuing to support the observational programs that are building the critical datasets, continuing to invest in the theoretical and computational tools needed to interpret those datasets, and continuing to train new scientists who will carry the investigation forward when the current generation moves on. It also means maintaining the intellectual integrity of the investigation by resisting the temptation to overclaim when the evidence is ambiguous. The history of anomaly investigations in science includes many examples where premature claims of discovery were followed by retractions when better data revealed the anomaly to be an artifact. The scientific community studying the Sagittarius A anomaly is well aware of this history and has been appropriately cautious in its public claims. That caution should be maintained as the evidence continues to accumulate, because the strength of the eventual conclusion will depend on the rigor with which the investigation was conducted throughout. The fifth element of the synthesis concerns the meaning of the investigation for our understanding of our place in the universe. This might seem like a detour from hard science into philosophy, but it is not. The question of what kind of universe we live in, whether its laws are complete and consistent, or whether there are gaps that future discoveries will fill, whether the structures we observe are the structures we think they are, or whether they harbor surprises at their most extreme edges, is a scientific question with practical consequences for how we develop physical theories and what observations we choose to make. The Sagittarius A investigation is testing whether the universe is the kind of place where classical black holes exist as perfect mathematical objects with smooth, featureless horizons that absorb information irreversibly, or whether it is the kind of place where compact objects at the mass and density of black holes have physical properties near their boundaries that deviate from the classical prediction in ways that preserve information or reflect matter rather than absorbing it. These are different kinds of universes with different implications for physics. A universe with perfect classical black holes is one where general relativity is complete in the domain of classical gravity, where the information paradox must be resolved by quantum gravitational effects that are too small to observe directly with electromagnetic astronomy, and where the near-horizon environment of accreting black holes is fully described by the combination of classical spacetime geometry and plasma physics without any need for quantum corrections at macroscopic scales. This is the universe that current physics predicts, and it is a universe that is internally consistent and experimentally well-supported in all regimes that have been tested. A universe where compact objects at the density of black holes deviate from the classical prediction at macroscopic scales is one where the resolution of the information paradox has observable consequences at scales accessible to electromagnetic astronomy, where quantum gravitational effects can influence macroscopic physics in ways that current theory does not predict, and where the near-horizon environment encodes information about the quantum structure of spacetime in observationally accessible signals. This would be a universe that is richer and stranger than the current framework predicts, and it would demand a fundamental revision of how quantum gravity connects to classical physics. The Sagittarius A investigation is the most sensitive test currently underway for distinguishing between these two kinds of universes at the scale of a supermassive black hole. It is conducting this test at a level of precision that was not achievable a decade ago, and that will improve substantially in the decade ahead. The test may not be fully conclusive within the current generation of instruments, but it is establishing the measurements and the methods that will make the test conclusive within the next generation. Understanding which kind of universe we live in has implications that extend throughout physics. If classical black holes are exactly what they appear to be, then the effort to develop quantum gravity can be focused on regimes that do not affect macroscopic electromagnetic astronomy, and the connection between quantum gravity and observation will remain primarily through cosmological measurements of the early universe and through the final stages of black hole evaporation that are not accessible to current instruments. If compact objects deviate from the classical black hole prediction at macroscopic scales, then the development of quantum gravity must account for observable effects at the scales of astrophysical black holes, and the program of constraining quantum gravity through astrophysical observations becomes central rather than peripheral. This is why the Sagittarius A investigation matters for theoretical physics as well as for astronomy. The outcome of the observational program will shape the direction of theoretical development for decades. A null result confirming the Kerr metric at percent-level precision and finding no evidence for echoes or surface emission will tell theorists that quantum gravitational effects at the scale of macroscopic black holes are smaller than current observational sensitivity and will focus their attention on mechanisms that produce only Planck-scale corrections. A positive result, finding a deviation from the Kerr metric or an echo signal, will tell theorists that macroscopic quantum gravitational effects are real and will demand the development of frameworks that can predict their magnitude and nature. Either outcome is scientifically valuable. The null result confirms and refines the current framework. The positive result demands its extension. Both outcomes advance understanding, though in different directions and at different speeds. The investigation of the Sagittarius A anomaly represents something important in the history of scientific inquiry beyond its specific content. It represents the moment when humanity's ability to observe the most extreme environments in the nearby universe caught up with the fundamental questions that those environments pose. For most of the history of general relativity, the theory predicted structures and phenomena that were observationally inaccessible. Event horizons, singularities, photon orbits, and the information paradox were mathematical features of solutions to equations, studied by theorists but untestable by observers. The gap between prediction and observation was so large that the theory was confirmed only in its weak field limit, at the precision achievable by solar system experiments and binary pulsar timing. That gap has been closing steadily over the past decade and is now approaching zero for the specific case of Sagittarius A. The shadow is resolved. The ring is detected. The centroid tracks during flares are measured at microarcsecond precision. The multiband variability is characterized across a range of timescales and amplitudes. The theoretical predictions are specific enough to be tested at the precision of current measurements. The correspondence between theory and observation is no longer confined to the weak field limit, but extends into the regime of strong curvature, where the most distinctive and most challenging predictions of general relativity apply. This closing of the gap between prediction and observation in strong field general relativity is one of the most significant developments in the history of the theory. It transforms black hole physics from a largely theoretical enterprise into an observational science with the same empirical grounding that other branches of astronomy have long enjoyed. The predictions of general relativity in strong gravity are now not just mathematically derived but observationally tested, and the testing is precise enough that deviations at the percent level are detectable. The Sagittarius A anomaly is the first specific tension in this newly observational regime, the first indication that the strong field behavior of gravity near a real compact object may not be exactly as simple as the classical theory predicts. Whether that tension resolves in favor of the classical theory or in favor of something new, it marks the beginning of a new era in which the deep predictions of general relativity and its alternatives are tested not just in the idealized cases where they were originally derived, but in the complex, hot, magnetized, dynamic environments where gravity actually operates in the real universe. This is the context in which the Sagittarius A anomaly should be understood. Not as an isolated measurement from one source, but as the first data point in a new regime of physics that is becoming observationally accessible for the first time. The next decade will add more data points, from better observations of Sagittarius A itself, from observations of other supermassive black holes with the next generation EHT, from gravitational wave measurements of compact binary mergers and extreme mass ratio inspirals, and from improved theoretical calculations that can predict the observable signatures of physics beyond the classical black hole model. The dataset will grow. The methods will improve. The theoretical frameworks will become more complete. The question that the anomaly has posed will eventually have an answer that is clear enough to be accepted by the community and significant enough to be incorporated into the standard understanding of what black holes are and how gravity behaves at its most extreme. The galactic center is not a distant abstraction. It is a specific place, 8,000 parsecs from the solar system, embedded in the same galaxy that contains our sun, our planet, and every human being who has ever lived. The black hole at its center has been there for billions of years, accreting at a trickle, flickering in infrared and radio, shaping the dynamics of the nuclear star cluster through its enormous gravitational influence. It has been doing these things throughout the entire history of life on Earth, long before any living thing had the capacity to notice or to wonder. The capacity to notice arrived only recently, in geological terms, when human civilization developed the mathematics of general relativity and the engineering of radio telescopes and infrared detectors and space observatories. The capacity to wonder arrived much earlier, in the instinct that looks at the night sky and asks what is there and why does it behave the way it does. The investigation of the Sagittarius A anomaly is the product of both capacities, the wondering and the noticing working together through the discipline of science to produce questions precise enough to be answered by measurements. The measurements are being made, right now, by teams of scientists on multiple continents, using instruments that represent the concentrated effort of thousands of engineers and scientists over decades of development. The data are being analyzed, right now, by researchers who are applying the best available mathematical and computational methods to extract the maximum information from photons that have traveled 8,000 parsecs to reach our detectors. The theories are being developed, right now, by physicists who are extending the mathematical framework of general relativity and plasma physics into regimes that have never before been observationally constrained. This is what the investigation looks like from the inside. Not a single dramatic moment of discovery, but a continuous process of measurement, analysis, and theoretical development that advances understanding incrementally and irreversibly. Each observation adds a data point. Each analysis refines the constraint. Each theoretical development sharpens the prediction. And the cumulative product of all this work is a picture of the near-horizon environment of Sagittarius A that is more detailed, more precise, and more physically complete than anything that existed at the beginning of the investigation. The picture is not yet complete. The anomaly is not yet explained. The question is not yet answered. But the direction of the investigation is clear. The tools are in place or being built, and the community has the knowledge and the commitment to follow the question wherever it leads. The investigation will continue until the answer is found, because that is what scientific investigations do when the question is important enough and the tools are adequate to address it. The center of the Milky Way will keep flickering. Sagittarius A will keep producing its quasi-periodic signals, its polarization rotations, its centroid tracks that loop and return in patterns that should not survive in turbulence but do. And the investigation will keep listening, with better instruments and better methods, until the signal is understood. The answer is in the flickering. It has always been there, encoded in photons that have been traveling toward us for 8,000 years, carrying information about the most extreme gravitational environment in our galaxy. We have only recently become capable of detecting those photons with sufficient precision to ask the questions they can answer. And we are asking them now, with everything we have. That is the story of the Sagittarius A* anomaly. A flicker at the center of our galaxy that turned out to be a question about the nature of black holes, gravity, information, and the deepest structure of physical reality. A question precise enough to be answered, an investigation rigorous enough to trust. And an answer that is coming, carried toward us at the speed of light from the heart of the Milky Way, encoded in the behavior of matter and energy and spacetime at the edge of the most extreme environment that the nearby universe provides. The flickering continues, so does the asking, and somewhere in the space between them, the universe is preparing its answer. We are ready to receive it.